Betelgeuse is not a star. Tonight, you can find it hanging from Orion's shoulder, glowing with a dull orange light that has watched over human history for thousands of years. But that tiny point in the sky is something far stranger. A few years ago, it suddenly changed, dimming so dramatically that astronomers around the world wondered if they were witnessing the beginning of its end. Yet the real story is hidden far beneath that turbulent surface, where forces powerful enough to tear worlds apart are playing out beyond our view. And there is an even stranger possibility. Betelgeuse is more than 600 light-years away. The light reaching your eyes tonight left before the invention of the telescope. The star you are looking at may still be alive, slowly approaching its final moments. Or it may already be gone, destroyed centuries ago, while its last messages continue crossing the darkness toward Earth. So which are we seeing tonight? A dying star, or the ghost of one that has already died? A star is not defined by how it looks. What defines it is a balance, a fight between two forces that has to stay almost perfectly even for as long as the star survives. Every particle inside it is being pulled toward the center by its own gravity, constantly, with no pause and no exception. Left alone, that pull would crush the entire structure down to a point in a matter of minutes. What stops that from happening is pressure pushing outward from the core, generated by nuclear fusion, hydrogen nuclei slamming together hard enough to fuse into helium and release energy in the process. For most of a star's life, those two forces are matched so precisely that its size barely changes for millions or even billions of years. That balance is the real definition, not the glow, not the steady position in the sky. The object marking Orion's shoulder still has the glow. Whether it still has the balance is a different question entirely. The correction is automatic, built into the physics itself, with no outside adjustment required. If a star's core contracts even slightly, the gas inside it compresses, the temperature rises, and the fusion rate climbs in response, pushing back outward until balance is restored. If the core expands slightly instead, the opposite happens. Fusion slows, pressure drops, and gravity pulls everything back in. A star spends most of its life inside that feedback loop, correcting itself thousands of times over without anyone watching, which is part of why it can sit at almost the same size and brightness for billions of years without drifting. Astronomers call this condition hydrostatic equilibrium, and the correction itself happens fast, far faster than the millions or billions of years it takes a star to burn through an entire supply of fuel. A pressure imbalance gets evened out in roughly the time it takes a sound wave to cross the star, typically somewhere between minutes and hours depending on its size, which is part of why the balance holds so reliably across timescales that dwarf it by a factor of 1 billion or more, the same kind of gap separating a single heartbeat from about 32 years of a heart beating without stopping. In the 1920s, the astrophysicist Arthur Stanley Eddington worked out the mathematics behind that balance in detail at a time when nobody yet knew exactly what was generating the outward pressure in the first place. Eddington proposed, in 1920, that some form of subatomic energy release inside stars had to be the source. Years before the precise mechanism, the fusing of hydrogen into helium was finally worked out by the physicist Hans Bethe in 1939. What Eddington got right immediately was the structure of the argument itself, that a star's size, its brightness, even its internal temperature, are not arbitrary properties. They fall directly out of the equation between how hard gravity pulls and how hard the core pushes back. The equations he derived are, in their basic form, still what astronomers use today to describe the inside of a star, including the inside of the one sitting on Orion's shoulder, a full century later. Nobody had ever measured the actual size of a star other than the Sun until December 1920, when the physicist Albert Michelson and the astronomer Francis Pease pointed an interferometer mounted on the 100-inch telescope at Mount Wilson directly at Betelgeuse and managed, for the first time in the history of astronomy, to measure the angular width of a star's disk. The number they got back exposed a deeper problem. Stars do not have a hard edge the way a planet or a billiard ball does. The gas simply keeps thinning outward until there is too little of it left to block any more light, so the surface astronomers actually measure is not a boundary at all. It is the depth at which the star finally becomes transparent to its own light. Which means nobody has ever actually seen the edge of this thing. Only the place where it stops being possible to see any further into it. A building has stood in one place for 100 years, recognizable by its outline to everyone who walks past it. At some point, deep inside the walls, a load-bearing beam begins to fail. The crack forms behind the plaster, where nobody on the sidewalk can see it. The building does not announce any of this. Its windows still catch the evening light exactly the way they always have. Everyone who walks by still calls it by the same name they have always used, because nothing about its outline has changed enough yet to make anyone reach for a different word. The building is still standing. A star runs on the same basic principle, except the load-bearing structure is not steel and concrete. It is the outward push of fusion balanced against the inward pull of gravity. When a star runs out of hydrogen at its core, that particular balance ends, and what happens next is more violent than it might sound. The core, with no fusion left to hold it up from inside, contracts under its own weight and heats further, hot enough to ignite a shell of hydrogen still surrounding it, burning in a thin layer rather than throughout the whole core the way it used to. That shell burns far more fiercely than the old steady core ever did, and the extra energy pours outward into the star's outer layers, forcing them to expand. The surface, now spread across a much larger volume, cools as it expands, shifting in color from white or blue-white toward orange and red. The star gets bigger and dimmer at the surface at almost the same time its interior is becoming more violent, not less, which is the opposite of what intuition usually expects from something described as dying. In a star massive enough, this is not a one-time shift. Once the helium in the core is also exhausted, the same pattern repeats. The core contracts again, heats further, and starts fusing the helium ash into carbon and oxygen, while the old hydrogen-burning shell keeps running further out. Massive stars build up a layered structure this way. Fusion shells stacked one inside another like the layers of an onion, each layer burning a slightly heavier element than the one above it, with the very center pushing toward elements heavier still. Betelgeuse is somewhere inside that sequence right now, well past the simple hydrogen-burning stage that the word star was effectively built to describe in everyday use. Astronomers call this stage a red supergiant, a star whose core has already burned through its original fuel and whose outer layers have swollen and cooled in response, turning the surface a deep orange-red, while the interior keeps fusing heavier material under conditions the original definition never anticipated. The constellation Orion holds it at the hunter's right shoulder, bright enough and red enough to be one of the easiest points of light in the entire winter sky to identify without any instrument at all. Betelgeuse carries the formal astronomical designation Alpha Orionis, a label that, by convention, is reserved for the brightest star in a constellation. The convention itself comes from the German astronomer Johann Bayer, who assigned Greek letters to the stars of each constellation roughly by brightness in his star atlas, published in 1603. Betelgeuse is not the brightest star in Orion. Rigel, marking the hunter's foot, outshines it most nights of the year. Rigel itself is a blue supergiant, a hotter, younger kind of star still burning hydrogen at a furious rate, behaving, for now, much closer to the simple definition of a star than the one carrying the brighter-sounding name. The label was assigned centuries ago, when measurements were cruder, and Betelgeuse, caught during one of its brighter pulses, may have briefly outshone its rival. The brightness has shifted since then, more than once. The name never did. A star that no longer runs on the balance the word was built to describe. A name that no longer matches the brightness it was assigned for, sitting on a catalog page since 1603. Both labels are still in use tonight, attached to the same point of light, neither one updated to match what is actually happening up there. So, what is the right word for something that fit an old definition for most of its life, and stopped fitting it before anyone agreed to retire the word? Replace the Sun with Betelgeuse, and Mercury disappears first. Venus goes next, then Earth, then Mars. Each one swallowed in turn as the new surface keeps expanding outward past the orbit that used to belong to it. Whether the swallowing stops at the asteroid belt or keeps going far enough to reach Jupiter depends on which measurement you trust and which moment in the star's slow pulsation you happen to catch it at, since the radius itself shifts as the star breathes in and out over the course of roughly a year. Different studies, using different instruments at different times, have put the edge anywhere from just beyond the asteroid belt to within reach of Jupiter's orbit itself. None of those numbers are wrong. They are measuring slightly different things, at slightly different moments, of an object that does not hold its outline still long enough to be pinned down to one number the way a planet can be. And despite all of this, despite a volume that could swallow 4 planets and threaten a 5th, Betelgeuse, seen from Earth's actual vantage point hundreds of light years away, occupies an angular size so small that for most of the history of telescopes, it was indistinguishable from any other point of light in the night sky. The same object that would consume the inner solar system very nearly disappears down to a single dot once the real distance separating it from us is factored in. Resolving even a sliver of that dot into something with an actual measurable disk, rather than just a brighter point among thousands of others, was exactly the achievement Michelson and Pease were attempting in 1920, and exactly why it counted as a breakthrough rather than a routine measurement. The breathing itself has a real physical cause, not measurement noise. As energy moves outward from deeper inside the star, certain elements in the outer gas become more opaque as they heat, trapping radiation underneath them and pushing that layer of gas outward. The layer expands, cools, becomes transparent again, lets the trapped radiation escape, and falls back inward, only to heat up and repeat the cycle. Astronomers call this a kappa mechanism, the same basic process that drives pulsation in several other classes of variable stars, though in Betelgeuse, the envelope doing the breathing is so large that one full cycle of swelling and contracting takes the better part of a year to complete. In the early 2000s, the astronomer Guy Perrin and his collaborators pointed an infrared interferometer at Betelgeuse and found something stranger than a simple size disagreement. A layer of gas, mostly water vapor, sitting well outside the boundary that visible light defines, sometimes extending half again as far out as the disk anyone would call the star's surface, depending on the study. Astronomers now call this extra shell a molecular layer, draped loosely around the star like a second, fainter atmosphere with its own separate edge, one that visible light mostly passes through unnoticed and infrared light catches instead. The same object, photographed in 2 different colors of light, hands back 2 different sizes. Think of it less like a ball with a boundary and more like fog that thickens gradually as you move toward the center, with no specific point where outside suddenly becomes inside. Walk into real fog on a dark road and there is no wall to hit, only air that keeps getting denser the deeper you go, until at some point you realize you can no longer see the headlights behind you. Betelgeuse works on the same principle, scaled up by a factor that fog has no business being compared to. There is no wall anywhere inside it either, only gas that keeps thickening the closer it gets to the center, all the way down to the region where fusion is still running. The gas out at the radius astronomers usually quote is remarkably thin. Past a certain depth, the density drops low enough that it would register as a better vacuum than most laboratories on Earth have ever managed to produce in a sealed chamber. For comparison, even the air, hundreds of kilometers up at the edge of Earth's atmosphere, thin enough that satellites coast through it for years without much drag, is still far denser than the gas marking the outer reaches of Betelgeuse. The star, at its outer reaches, barely qualifies as a fluid at all. It is closer to an extremely faint haze that happens to be glowing, held loosely in place by gravity strong enough to keep it from drifting off into space, but not dense enough to behave like the gas anyone breathes. Betelgeuse, for all of this, is not even the largest star currently known. Stars, such as VY Canis Majoris and UI Scuti, both red supergiants farther away and harder to measure precisely, have been estimated at various points to be several times larger still, with radius figures for each swinging just as widely across different studies for exactly the same underlying reason. The difficulty that makes Betelgeuse's exact size hard to pin down only gets worse as the star in question grows larger and more distant. Ranking the biggest known stars in the galaxy is less a settled list and more a moving target that shifts with every new generation of telescope. If Earth's orbit still existed at its current distance with Betelgeuse in the Sun's place, there would be nothing solid to stand on at that distance to notice the difference. The planet itself would already be gone, consumed along with Mercury, Venus, and Mars, somewhere inside gas so sparse that a spacecraft passing through it might barely register the encounter on a sensor built to detect atmospheric drag, even while sitting deep inside what astronomers would still call, technically, the body of the star. Whatever clock divides a year into months and seasons on this planet exists only because Earth completes one full lap around the Sun at the distance currently called home. Move the central light source out to where Betelgeuse's outer atmosphere now sits, and that lap, that calendar, that entire way of measuring a year would not have anywhere left to happen. A car does not become a city by getting bigger. At some point, the word stops applying and a different word takes over. A star expanding by a factor of 1,000 in radius keeps the same name the whole way through, even as the physical reality underneath that name changes almost beyond recognition. Despite occupying a volume that could swallow 4 planets and brush against a 5th, Betelgeuse contains only a modest multiple of the Sun's mass, somewhere in the range of 15 to 20 times as much material, not thousands of times more, the way the volume increase alone might suggest. Spread that same modest amount of extra mass across a volume that size, and the average density across the whole star works out lower than the air filling an ordinary room by a margin large enough that comparing the two as a simple ratio barely makes sense. Almost all of that enormous size comes from how loosely the material is spread out, not from how much material is actually there. A star this big is, by mass, barely a heavyweight at all. Brightness and mass are not telling the same story here. Something hot enough and luminous enough to be visible without any instrument from hundreds of light years away turns out, when actually weighed, to be barely substantial enough to call solid. When Michelson and Pease made that first measurement in 1920, the distance estimate available to them at the time translated their angular reading into a physical radius only a few hundred times the radius of the Sun. As distance estimates to Betelgeuse have been revised across the century since, that same kind of angular measurement has translated into physical sizes several times larger than what 1920 originally implied, without the star itself necessarily growing by anything close to that much in the meantime. A good portion of the number grew because the ruler changed, not because the object being measured did. So the real question is not how something gets this large. Mass and gravity and the failing balance from before account for that well enough. The harder question is, What a structure spread this thin, this loosely held together, is actually doing on its outer layers right now, where the gas is faint enough to count as nearly nothing, and yet still somehow organized enough to hold a recognizable shape. Heat does not travel from the core of a star to its surface in a straight line. For the outer portion of most stars, radiation alone cannot move energy outward fast enough, so the gas itself starts physically moving instead, hot material rising toward the surface, cooling, and sinking back down to be reheated, over and over, in a cycle called convection. On the Sun, this produces granulation. Millions of individual convective cells covering the visible surface at any given moment, each one roughly the size of a large country on Earth, each one lasting somewhere between 8 and 20 minutes before breaking apart and reforming. At any given instant, something on the order of 4 million separate granules cover the Sun's visible disk, each completing its full rise and fall so quickly that the entire surface effectively repaves itself with new cells thousands of times over the course of a single human lifetime. Photographed up close, the surface of the Sun looks like the top of a pot of boiling soup, a fine, constantly shifting texture of bright rising centers and darker sinking edges. Betelgeuse does not look like that. Surface gravity is the variable that decides how large a single convective cell is allowed to get before it breaks apart, and Betelgeuse's surface gravity is almost nothing by comparison. Mass divided by the square of an enormous radius works out to a surface pull roughly tens of thousands of times weaker than what holds the Sun's granules to a country-sized scale. With gravity barely confining anything, the physical distance over which pressure changes significantly, what physicists call a scale height, stretches out dramatically, and convective cells tend to organize themselves at roughly that same enormous scale. Instead of millions of small bubbles, the math points toward a small number of cells, potentially just a handful, each one large enough to cover a meaningful fraction of the entire visible surface. For a long time, the working assumption was that any star's surface would look like a scaled-up version of the Sun, the same fine granulated texture, repeated at a different size depending on the star's particular gravity. The actual data broke that assumption rather than confirming a more extreme version of it. Betelgeuse's surface is not the Sun's surface scaled up. It is a different regime entirely, one where the texture coarsens until it stops looking like texture at all and starts looking instead like a small number of distinct, individually trackable structures. In 2002, the astronomer Bernd Freytag and his collaborators ran three-dimensional simulations of convection in a red supergiant envelope and produced exactly that result on a computer, a handful of giant cells dominating the surface, years before anyone had direct observational proof that real stars actually look that way. The confirmation came in 2009, when Xavier Haubois and his team used the AMBER instrument on the Very Large Telescope Interferometer in Chile to reconstruct an actual image of Betelgeuse's surface from interferometric data. A single telescope, even a large one, cannot resolve enough detail on something this far away to show individual bright and dark patches rather than just an overall blur. An interferometer works around that limit by combining light collected from several separate telescopes at once, spaced widely apart, using the precise differences in when the light arrives at each one to reconstruct detail, far finer than any single instrument could manage alone, effectively turning a handful of telescopes scattered across a mountaintop into one telescope as wide as the distance separating them. The image that came back showed exactly what the simulations had predicted years earlier, not an even, granulated texture. A small number of distinct bright patches, irregular in shape, scattered unevenly across the disk, with as few as 2 or 3 regions accounting for a significant share of the star's total light output at the time of that particular observation, some of them individually large enough to span a meaningful fraction of the star's entire visible hemisphere. Later observing campaigns, using different wavelengths and different equipment, have refined the exact count and shape of these patches without overturning the basic picture. The precise number shifts depending on which method is used, but a small number of enormous cells, rather than a fine, granulated texture, has held up consistently across every approach tried since. Picture a pot of soup again, but scaled up until it holds an ocean's worth of liquid, and where the sun's pot produces millions of fist-sized bubbles breaking the surface every few minutes, this pot produces 3 or 4 bubbles the size of countries, each one rising and falling over the course of months rather than minutes. The physics underneath both pots is identical. Hot fluid rises, cools, sinks, repeats. What changes is the scale the physics is allowed to operate at, and that scale depends entirely on how hard gravity is squeezing the system. Weaken the squeeze enough, and the same boiling process that produces a fine, busy texture on one star produces a handful of slow, lumbering giants on another. The practical consequence is a star whose brightness is not evenly distributed and does not stay still. A single one of these convective cells, rising hot and bright toward the surface, can measurably brighten one entire region of the disk, while a neighboring cell, sinking and cooling, dims another. The temperature difference between a rising patch and a sinking one can run into the hundreds of degrees, more than enough on its own to noticeably change how much light a given patch of surface gives off, since brightness scales steeply with temperature for anything glowing this hot. The sun's granulation pattern is so fine and so evenly distributed across millions of cells that its overall brightness barely flickers from this process at all, the small fluctuations from individual granules averaging out across the whole disk before anyone watching from a distance could notice. A star with only a handful of enormous cells does not get that luxury of averaging. When one giant cell is rising and another happens to be sinking at the same time, on the same hemisphere, the imbalance is large enough that it can show up directly in how bright the star appears from any distance, including a distance of hundreds of light years. Observers working with the American Association of Variable Star Observers have logged Betelgeuse's apparent brightness by eye and later by instrument for more than a century, building one of the longest continuous brightness records kept for any star in the sky. That record shows real movement across the decades, rises and dips of a noticeable but generally modest size, broadly consistent with a handful of giant cells slowly rearranging themselves across the visible hemisphere over months at a time. There is something specific worth noticing in how differently the same underlying mechanism behaves once gravity stops doing its usual job of keeping things small and numerous. A process responsible for nothing more dramatic than moving heat outward. The exact same process running quietly under the sun's surface every second of every day becomes something closer to a slow, visible pulse once the star is large enough and loose enough to let it. Each of those giant cells is itself a temporary structure, rising, spreading, cooling, and eventually being replaced by the next one, on a timescale of months rather than minutes. The gas inside each cell is not drifting lazily while it does this. Simulations of these enormous convective flows put the rising and sinking speeds at several kilometers per second, fast enough that a single parcel of gas covers a distance comparable to the radius of the entire solar system over the course of one cycle, even though the full rise and fall still takes months, simply because of how far that gas actually has to travel to get anywhere on a structure this size. A handful of enormous cells, slowly cycling across a surface large enough to swallow the inner solar system, with no fine averaging to smooth out the differences between them, sets up a star whose total brightness has every reason to drift, sometimes by a little, depending entirely on which cells happen to be rising and which happen to be sinking on the side currently facing Earth. What nobody had fully worked out, watching that surface for most of the 20th century, was how far that drifting could actually go, and what it would take for one of those drifts to stop looking like ordinary variation and start looking like something else entirely. By October of 2019, Betelgeuse had dropped below the bottom of its normal brightness range, and nobody watching yet knew why. For most of the century that observers had been tracking it, Betelgeuse's apparent brightness drifted in a fairly narrow, familiar band. Never quite as bright as Rigel, but reliably one of the dominant points of light in Orion, easily outshining the fainter stars, marking the hunter's other shoulder and belt. Smaller dips of a similar kind had shown up before in the historical visual record, including episodes noted in the 1920s and again in the 1940s, though none of those earlier dips had been tracked with anything close to the instrumental precision available by 2019, leaving only rough, second-hand impressions of how deep they actually went. The same network that had spent 100 years logging its ordinary ups and downs through the American Association of Variable Star Observers was the one that flagged this particular dip as unusual almost as soon as it started, well before it became the faintest reading anyone had on record. It kept dropping. The astronomer Edward Guinan at Villanova University filed the first formal alert through the Astronomers' Telegram network in early October, flagging brightness already below the bottom of the star's documented range, and the readings kept falling through November and into the new year rather than leveling off the way a single ordinary dip usually would. By February of 2020, Guinan and his colleagues measured Betelgeuse at roughly magnitude 1.6, the faintest value in their entire 25-year photometric record, and, as far as anyone could tell from the historical data available, the faintest Betelgeuse had been in over a century of monitoring. A star that normally sat around magnitude 0.5 had lost somewhere close to 2/3 of its usual brightness, a large enough change in such a familiar object that it stopped being a number on an astronomer's chart and became something anyone could check for themselves by walking outside and looking up. Guinan's team checked the result against several comparison stars nearby in the sky, stable, well-calibrated stars used specifically to rule out instrument error. None of the comparison stars showed any unusual change, which confirmed the dip belonged to Betelgeuse specifically and was not an artifact of the equipment doing the measuring. Bellatrix, the star marking Orion's other shoulder, normally sits well behind Betelgeuse in brightness, fainter by a wide enough margin that the difference is obvious without any instrument. During the dimming, that comparison flipped. For a stretch of weeks, Bellatrix outshone Betelgeuse, an arrangement nobody alive had ever seen in that constellation, confirmed independently by amateur observers across multiple continents, simply by glancing up and noticing that the hunter's two shoulders no longer looked the way they were supposed to. Ordinary phone cameras turned out to be sensitive enough to catch the difference too, and side-by-side comparison photos of the two stars circulated widely, evidence anyone could gather for themselves without owning a single piece of professional equipment. A lamp in a familiar room grows dimmer over several weeks, with nobody touching the switch and nobody able to explain why the light keeps fading. The room does not go dark all at once. The change happens slowly enough that anyone glancing at it on any single night might not notice anything wrong, and only becomes undeniable once enough nights have passed to compare against memory. That was roughly the experience of watching Betelgeuse through the final months of 2019, a familiar fixture growing visibly fainter on a timescale of weeks, with no obvious cause and no working dial inside the room to explain the drop. Most astronomers studying the object stayed considerably more cautious, for reasons rooted in everything covered earlier on how this kind of star actually behaves. A star can dim sharply without dying. A true final collapse does not unfold as a gradual fade spread across several months. Once a massive star's core actually runs out of fuel to fuse, the last stages move at a completely different pace, the final phase of fusion before collapse lasting on the order of a single day, and the collapse itself, once it actually begins, compressing the core down in well under a second. Nothing in the established physics of how a star like this dies matches a slow, months-long dimming visible from Earth. Whatever the dimming turned out to be, the timescale alone, weeks and months rather than hours, already argued against it being the literal opening act of a collapse well before anyone had assembled a more specific explanation. A star whose enormous, slow-moving convective cells were already known to rearrange themselves over months, the same mechanism catalogued in detail years earlier, had an obvious, far less dramatic candidate explanation sitting right there in the existing data, alongside everything established earlier about how slowly a star's internal balance actually shifts compared to a single season of changed appearance. The dimming was not even across the disk. The astronomer Andrea Dupree at the Harvard-Smithsonian Center for Astrophysics had already turned the Hubble Space Telescope toward Betelgeuse to monitor it in ultraviolet light, and the data coming back showed something asymmetric happening, a region in the southern part of the star behaving differently from the rest in the weeks immediately before the dimming became visible to the naked eye. What exactly that asymmetry meant, and what it would take to connect an unusual ultraviolet reading to a 2/3 drop in visible brightness months later, was not yet settled, even to the team gathering the data in real time. Word of the dimming spread quickly enough through the professional community that observing time on instruments around the world, normally booked months or years ahead, got rearranged to fit Betelgeuse in. Within weeks, data was arriving from observatories on multiple continents and in multiple wavelengths at once, an improvised campaign assembled faster than any single observatory's normal scheduling process would typically allow. Dust formation itself was not a new idea invented to explain Betelgeuse specifically. Red supergiants are already known, from decades of study across many such stars, to shed material from their outer layers from time to time, material that can cool and condense into genuine dust once it drifts far enough from the star's heat. If something along those lines had happened here, it would not be a new kind of behavior for this category of star. It would simply be the first time anyone had caught one doing it, on this particular star, in enough detail to actually watch it unfold. Whatever caused this, it did not happen in October of 2019. The light-reaching telescopes and backyard observers that month had already been traveling for centuries, so the actual physical event being recorded, whatever it turns out to have been, took place on the star itself, long before anyone watching Orion that autumn was even born. The dimming on the calendar marking only the moment the news finally arrived, not the moment it happened. Anyone who had ever looked up at that exact point in the sky on any clear night across the preceding several centuries, astronomer or not, had been looking at light already carrying this story toward them, long before there was an instrument on Earth sensitive enough to notice anything had changed. Two explanations were on the table once the initial panic faded, and the data available at the time did not rule out either one. One pointed to the surface itself, an unusually large convective cell cooling and sinking out of view, exactly the kind of behavior already confirmed as possible for a star with only a handful of enormous cells instead of millions of small ones, a cell simply happening to turn its cooler face toward Earth at an unlucky moment. The other pointed somewhere else entirely, towards something the star may have actually shed, a cloud of fresh material sitting between Betelgeuse and every telescope on Earth, blocking light, rather than the star itself producing any less of it. Either explanation fit the timescale. Neither one, on its own, fully explained everything the ultraviolet data from earlier in the year seemed to be hinting at. The answer turned out to be both, in an order neither hypothesis on its own had considered. Dupree's team had been collecting ultraviolet spectra of Betelgeuse with Hubble's Space Telescope imaging spectrograph for months before the visible dimming ever started, tracking specific wavelengths of light, particularly a pair of magnesium emission lines that act as a reliable tracer of material in a star's outer atmosphere. In data gathered in early 2019, months before anyone noticed anything unusual through an ordinary telescope. Those spectra already showed something moving. Material absorbing light at wavelengths shifted toward the blue end of the spectrum, the signature of gas traveling outward, toward Earth, rather than sitting still on the star's surface. The shift in those lines suggested material moving at speeds reported to be on the order of 200,000 miles per hour, fast enough to put real distance between itself and the photosphere within a matter of weeks. By September, the southern hemisphere of the star had grown noticeably darker in ultraviolet light specifically, well before the visible light dimming most people eventually noticed had even begun. Something had already left the surface months earlier, expanded outward, and cooled as it moved farther from the star's heat, cool enough by the time it had traveled far enough to condense directly out of gas into solid grains of dust. The same basic physics turns water vapor into clouds on Earth, molecules slowing down and sticking together once the surrounding temperature drops low enough, just operating here on rock, forming elements like silicon and oxygen instead of water, at temperatures and pressures that only exist in the stretch of space immediately around a star this large. That fresh dust, sitting in the line of sight between Betelgeuse and every telescope on Earth, was what actually blocked the light starting in October. The visible dimming was not the star itself growing fainter. It was new material, ejected months earlier, finally cool enough and dense enough to cast a shadow. Follow-up observations in infrared light, sensitive to the specific chemical fingerprint of different kinds of dust, identified the newly formed material as silicate grains, the same basic family of minerals that makes up most of Earth's rocky crust, condensing here directly out of stellar gas rather than ever having existed as part of a solid planet. The composition matched what existing models of red supergiant mass loss had already predicted such ejected material should turn into, once it cooled far enough from the star to allow solid grains to form. Dupree's spectroscopy was not the only line of evidence pointing to this conclusion. In 2021, the astronomer Miguel Montarguez and his team published direct images of Betelgeuse taken with the Sphere instrument on the Very Large Telescope, comparing pictures of the star's disk taken before, during, and after the dimming. The images showed exactly the pattern the spectroscopy had implied. The southern portion of the visible disk measurably darker during the dimming than the rest of the star, consistent with a discrete patch of obscuring dust rather than an even, all-over dimming of the kind an actually cooling surface would produce. Montarguez and his team had a baseline image from January of 2019, taken for an unrelated project, well before anything unusual had been noticed. A second image, taken that December, showed the southern third of the disk visibly darker than it had been less than a year earlier. A third image, taken the following March, showed brightness beginning to return to that same region, consistent with the obscuring cloud gradually drifting clear of the line of sight. Two completely different techniques, an indirect reading of light shifted in wavelength and a direct photograph of the disk itself, converged on the same physical picture independently. For a category of star already known to leak mass slowly over millions of years through a steady stellar wind, catching one sudden, large-scale ejection in this much detail, with spectroscopy and direct imaging in agreement, gave astronomers their first real look at a single mass loss event actually happening, rather than inferring the overall pattern from gas and dust already scattered across a wide region long after the fact, which is how most prior evidence for red supergiant mass loss had been gathered. Picture a bruise instead of a dimming lamp. The actual injury, the broken vessels under the skin, happens at the moment of impact, invisible at first. The discoloration anyone can see only shows up later, once enough blood has pooled and broken down under the surface to change color, and by the time it's visible, the original bog injury already happened in the past. Betelgeuse worked the same way. The real event, gas physically leaving the star, happened months before anyone watching from Earth had any way of knowing. What people eventually saw and worried about was the visible aftermath, arriving late, the equivalent of the bruise's color rather than the impact itself. The darkened region covered roughly a quarter to a third of the star's entire visible disk, a patch of surface that, on an object already established as large enough to swallow 4 planets, was on its own larger in absolute area than the Sun's entire visible disk many times over. A single localized event, confined to one hemisphere of one star, was large enough in absolute terms to count among the biggest individual structures ever directly tracked moving through any star's atmosphere. Astronomers now call an event like this a surface mass ejection, deliberately echoing the language used for a much smaller, much more familiar phenomenon on the Sun, a coronal mass ejection, the sudden release of material from the Sun's outer atmosphere that drives space weather and occasionally disrupts satellites and power grids on Earth. Calling Betelgeuse's event by the same basic name does not mean the two are the same size. It means the underlying physics, material breaking free from a star's gravity and outer magnetic structure and escaping into space, is recognizably the same process, just operating on an entirely different scale, a comparison worth holding on to for what comes next. Calling this a wound rather than a death is not just a softer way of describing the same event. The star bled, in its own sense of the word, and then stopped bleeding, and kept operating largely as it had before, which is a meaningfully different story than the one most of the original headlines were telling. The finding also reset what astronomers now watch for. Before 2019, a sudden dramatic dimming on a star like this was the kind of event that, by default, raised the word supernova in casual conversation. After Dupree and Montarget, there is now a confirmed, documented, considerably less dramatic alternative on file, an actual precedent rather than a theoretical possibility, which means the next unexplained dip in Betelgeuse's brightness will be measured against a real prior case instead of pure speculation. What actually triggered the ejection remains uncertain. The leading idea connects it to the convective cells already noted as covering Betelgeuse's surface in only a handful of enormous patches. One particularly vigorous upwelling, a plume of hot gas rising with more force than usual, may have pushed material past the point where the star's weak surface gravity could pull it back, launching it outward instead of letting it fall back the way the slower, ordinary cycle described earlier usually works. A competing idea ties the ejection to the same pulsation cycle responsible for the star's slow breathing, the outward push of an expanding phase potentially adding just enough extra force to a convective plume already close to escaping on its own. Neither idea has been confirmed over the other, and it remains entirely possible both effects contributed at once. Confirming the exact trigger either way would require catching another such event in progress, watching the moment of ejection itself rather than reconstructing it afterward from the dust and the dimming it left behind. So the star was not cooling. Something had already happened to it, and the entire visible event that worried so many people watching from Earth was the slow arrival of evidence for an injury that had occurred and then gone quiet long before anyone here noticed anything was wrong. The mass involved in that single ejection has been estimated at roughly 400 billion times the mass of a typical coronal mass ejection from the Sun. That comparison only means something once both sides of it are actually pictured. A typical solar CME carries away something on the order of 1 billion tons of material, an amount that sounds enormous in isolation and actually is, by any everyday human measure, but the Sun produces CMEs of roughly that size on a fairly routine basis, several a week during active periods, without it costing the Sun anything noticeable in its overall structure or behavior. What left Betelgeuse in this single event has been estimated at several times the mass of the Moon, ejected not over years of routine activity but in one episode, tied to the single surface eruption described earlier as the actual cause of the dimming. If a typical solar CME is a hard exhale, this was closer to emptying an entire ocean's worth of water in one motion. Picture the Atlantic Ocean, all of it, every drop, leaving the Earth in a single outward push rather than draining slowly over centuries. The image is useful for the scale of the act, not for the physics, since an ocean of water and a cloud of stellar gas behave nothing alike once they actually start moving. The real number underneath the image is the one that matters. Several lunar masses, gone from the star's outer layers, in one event, rather than the steady trickle most red supergiants lose over millions of years. For a sense of what the Sun's biggest known outbursts actually look like, the closest comparison most people have heard of is the Carrington event, a colossal solar storm in September of 1859, named for the astronomer Richard Carrington, who happened to be observing sunspots through a telescope at the exact moment an enormous flare erupted. The coronal mass ejection that followed reached Earth in under a day, triggering auroras bright enough to be seen as far south as the Caribbean, and inducing electrical currents strong enough to set some telegraph stations on fire. Accounts from the period describe auroras bright enough that some witnesses claimed they could read a newspaper outdoors at night by the light alone, far outside the polar latitudes where auroras are normally confined. It remains, in the historical record, the most powerful geomagnetic event ever documented striking Earth. Even an event on that scale, the single most extreme outburst the Sun has produced in recorded human history, falls nowhere close to the material involved in what left Betelgeuse in 2019. The Carrington event would not register as a meaningful fraction of it. It would barely register as a rounding error. Every aurora ever photographed, every satellite ever knocked briefly offline by a geomagnetic storm, every account of a particularly active solar cycle disrupting radio communication traces back to outbursts that are, in raw material terms, almost unimaginably gentle compared to the single event already established as the cause of Betelgeuse's dimming. Among every stellar mass ejection event ever directly characterized through both spectroscopy and imaging together, this one remains the largest on record, not just larger than anything ever measured from the Sun, but larger than any comparable event caught and confirmed in this much detail on any other star studied so far. Despite all of that, several lunar masses is still a vanishingly small fraction of Betelgeuse's own total mass, a star already shown as carrying somewhere around 15 to 20 times the mass of the Sun. The fraction actually lost works out to something less than 100 millionth of the star's entire inventory of material, gone in a single event that, by any human standard, or by the standard of anything the Sun has ever produced, counts as catastrophic. Nothing resembling an event this size has ever been recorded happening to the Sun, and the consequences of one actually occurring there are difficult to model with any real confidence, since the closest available comparison, the Carrington event, sits so many orders of magnitude below it that extrapolating forward carries enormous uncertainty. What is certain is that the inner solar system, accustomed to outbursts measured in mere billions of tons rather than lunar masses, has never had to weather anything in this particular weight class. The ejected material itself did not simply vanish once it left the star. Spread thin now across an expanding shell of gas and dust moving outward from Betelgeuse, it remains, in principle, traceable for years or decades to come, slowly cooling and dispersing into the surrounding environment, rather than ever falling back onto the star it came from. Material moving outward at roughly 200,000 miles per hour, the speed already given for the ejected gas, covers an enormous distance quickly by everyday standards, even though the scale of the star itself means that distance still represents only a modest fraction of the full journey toward open interstellar space. By now, the bulk of that material sits many times farther from the star than the star's own enormous radius, well clear of the photosphere, continuing to expand and thin as it travels. What happened to Betelgeuse has also reshaped how astronomers think about red supergiants approaching the ends of their lives more broadly. Existing models of how these stars lose mass before an eventual collapse had mostly assumed slow, continuous winds doing the bulk of the work over millions of years. A single confirmed episode of discrete, catastrophic mass loss. This large raises the possibility that at least some portion of the total mass a red supergiant sheds over its lifetime happens in occasional violent episodes rather than a steady drip, a real shift in how the final stretch of a massive star's life may need to be modeled going forward. Mass alone does not capture the full picture either. Moving several lunar masses outward against a star's own gravity takes a correspondingly enormous amount of energy that has to come from somewhere inside the star's own structure, and current estimates put the total energy released in the event at levels that make even the most violent solar flares on record look like background noise by comparison. Putting a precise number on that total energy remains difficult, since it depends on assumptions about the ejected material's exact speed and density that are still being refined, but every published estimate so far lands in a range that dwarfs the energy of the largest solar flares ever recorded by many orders of magnitude, the kind of gap where direct comparison stops being especially meaningful past a certain point. Exactly how a convective plume or a pulsation cycle, on their own or working together, could supply that much energy in one localized burst remains an open question, feeding directly into the uncertainty already raised about what triggered the ejection in the first place. How often a red supergiant produces an event of this size is itself unknown. Betelgeuse has been watched closely enough, for long enough, that an event this dramatic happening more than once or twice a century would likely have left some trace in the historical record, yet nothing remotely this size shows up in over 100 years of careful brightness monitoring before 2019. Whether that makes it a once-in-a-generation event for this particular star or something closer to a once-in-many-centuries event is not something the current data can answer with any confidence. Catching it at all required exactly the kind of continuous, decades-long monitoring already established earlier. The same century of patient record-keeping that first noticed the dip, layered on top of a space telescope happening to be pointed in the right direction at the right time. A rarer event would likely have simply been missed. A wound this size does not necessarily end a story. The next question is what a star does after losing that much material from its own surface in one motion, and whether anything about it looks the same afterward as it did before. Betelgeuse did not simply return to normal. Brightness climbed steadily through the rest of 2020, passing back through its ordinary range within months, the way a clean recovery should look after a single large ejection finished clearing the line of sight. It kept climbing past that point. By 2023, multiple independent observing campaigns were reporting Betelgeuse at the highest brightness recorded in the star's entire history of careful monitoring, roughly 50% above its typical historical average, outshining its own ordinary peak by a wide enough margin that, for a stretch of months, it rivaled Rigel directly for the title of brightest star in Orion, an arrangement that had not occurred in living memory of anyone tracking the constellation. Ordinary pulsation alone, the same roughly year-long breathing cycle noted earlier, produces some natural variation in brightness from one cycle to the next on its own. The 2023 peak exceeded not just the star's average brightness, but the upper edge of that normal pulsation range as well, ruling out an ordinary cycle, simply caught at an unusually bright moment as a sufficient explanation by itself. Edward Guinan, the same astronomer whose team first flagged the dimming back in 2019, continued tracking the recovery and confirmed the trend held up across multiple independent photometric systems rather than being an artifact of any single instrument or observing team. A star that loses a chunk of its outer material and then settles back into its old routine is a tidy story. A star that loses material and then becomes brighter than it has ever been recorded, on the far side of that loss, is not. A dust cloud clearing from the line of sight explains a return to the star's ordinary brightness range well enough. It does not, on its own, explain brightness pushing well past anything recorded before the dimming ever started. Removing an obstruction restores a view. It does not make the thing being viewed brighter than it ever was before the obstruction existed in the first place, not without something else also changing. Picture a scar instead of a wound closing flat. Skin that heals after a deep enough injury rarely returns to exactly what it was before. Scar tissue is denser, often thicker than the surrounding skin ever was, built from collagen laid down in a different pattern than the original structure it replaced. The body does not restore the old configuration. It builds a new one, on top of where the old one used to be. Something analogous appears to have happened to Betelgeuse's outer layers. The convective structure previously established as covering its surface in a handful of enormous cells did not necessarily snap back into its pre-dimming arrangement once the ejected material cleared. Whatever reorganized after losing that much mass from one hemisphere may have settled into a configuration that radiates more efficiently or differently than the one it had before, an actual structural difference rather than a simple return to form. That is not the only explanation on the table. One competing idea does not require the star's interior to have changed at all. Betelgeuse, like most red supergiants, normally sits inside a faint, persistent shell of its own circumstellar dust, material shed gradually over a very long time, dimming the star very slightly, even under ordinary conditions. If the violence of the ejection disrupted or partly cleared that ordinary background shell along with producing the dramatic new cloud responsible for the dimming itself, the star could simply be appearing brighter than usual because less of its normal light is being absorbed by dust that would typically be in the way. No actual change to the star's own light output required. The two explanations make different predictions about a third piece of evidence, which is part of why it matters. Reduced dust along the line of sight would explain extra brightness without touching anything about the star's internal rhythm. A genuine structural change to the outer layers would be expected to leave a mark on exactly that rhythm. There is evidence the star's underlying rhythm itself shifted, not just its brightness. Researchers tracking the timing of Betelgeuse's regular pulsation, the same roughly year-long breathing cycle established earlier as driven by the kappa mechanism, have reported the period running measurably shorter since the dimming than it did beforehand, though the precise size of that shift and how confidently it can be measured against the star's already somewhat irregular cycle remain points of ongoing discussion. A pulsation period is not supposed to be an easy thing to change. It depends on the star's overall structure, its size, its density profile, the balance of forces governing how the whole envelope expands and contracts. A measurable shift in that rhythm leans against the simpler dust-only explanation and toward the idea that the ejection altered something more fundamental than just the surrounding dust. Astronomers did not have to guess about whether the surface itself looked different. The same interferometric imaging techniques already used to map the original handful of giant convective cells were turned on Betelgeuse again after the recovery, producing fresh reconstructions of the visible disk to compare directly against the earlier maps. Early comparisons suggest a surface broadly similar in its basic pattern, still a small number of large, bright patches rather than fine granulation, but with enough differences in the precise size, number, and position of those patches that ruling out a genuine reorganization rather than coincidence or measurement noise will require more observing seasons to settle properly. Nothing requires picking only one explanation over the other. A star that just shed several lunar masses of material plausibly disrupted both its own immediate surroundings and the convective structure generating its light at the same time, in which case the unusual brightness and the unusual rhythm could simply be two visible symptoms of a single underlying disturbance rather than two competing stories that need to be ranked against each other. Anyone glancing up at Orion sometime in 2023, with no idea any of this had happened, would simply have noticed Betelgeuse looking unusually bright, a small, naked-eye change requiring no equipment and no background knowledge to spot, the same way the dimming itself had once been noticed by people with no professional stake in the star at all. The public reaction inverted itself, along with the brightness. Where headlines in early 2020 had asked whether the star was about to die, headlines in 2023 asked something closer to the opposite, whether an unusually bright, unusually active Betelgeuse might be evidence of exactly the kind of pre-collapse instability the dimming itself had already been largely ruled out as showing. The same object, doing the reverse of what frightened people 3 years earlier, ended up feeding very similar speculation, even though brightening and dimming, on their own, say very little about how close any star actually is to the end of its life. Whether the extra brightness is spread evenly across the disk or concentrated unevenly, the way the original dimming was concentrated specifically in the southern hemisphere is itself still being mapped. An uneven brightening would argue more strongly for a genuine structural change confined to one region of the star, rather than a star uniformly less obscured by dust on every side at once. Continued monitoring has not yet settled which explanation is correct. If the brightness gradually fades back down toward its pre-dimming average over the coming years, that would favor the simpler dust explanation, a temporarily cleared sightline slowly refilling with fresh material, the way it presumably did before the ejection ever happened. If the brightness instead stabilizes at this new, higher level rather than fading, that would argue for a lasting structural change, a new equilibrium rather than a temporary window. As of the most recent available data, the star has not yet definitively chosen between those two futures. A star that erupts, loses several lunar masses, and comes back not just intact but altered, brighter and running on a changed internal clock is not behaving like an object settling quietly toward old age. The next uncomfortable question is what else about it might not be settling the way anyone assumed either. Doppler measurements of Betelgeuse's surface point to something rotating faster than the physics of an expanding star is supposed to allow. Angular momentum. The physical quantity that governs how fast a spinning object turns depends on both how fast something is moving and how far that mass sits from the axis it is spinning around. Left alone, with nothing pushing or pulling from outside, that quantity stays constant. Pull mass in closer to the axis, and rotation speeds up to compensate. Push mass farther out, and rotation has to slow down. The same total amount of spin spread across a much larger radius. A figure skater pulling both arms in tight spins dramatically faster, not because any new force started pushing them, but because the same rotation is now concentrated into a much smaller radius. Extend the arms back out, and the spin slows immediately. The same total angular momentum now spread across more distance from the body's center. Every skater who has ever performed that spin is demonstrating, without necessarily knowing it, one of the more reliable conservation laws in physics. A star evolving from a compact, fast-burning progenitor into a red supergiant hundreds of times larger should behave the same way, just on a scale no skater could match. Whatever rotation rate the star's much smaller, much younger version carried on the main sequence should have slowed dramatically as the outer layers swelled outward to their current enormous radius, the same conservation of angular momentum spreading whatever spin existed across a sphere that ballooned by a factor in the hundreds. By the math, Betelgeuse ought to be rotating so slowly today that detecting any rotation at all would be a genuine technical challenge. That is not what the data shows. Spectroscopic measurements of the star's surface, tracking how light from one side of the disk shifts slightly toward the blue and light from the other side shifts slightly toward the red, The signature of one edge approaching and the opposite edge receding as the whole structure turns indicate a rotation considerably faster than the simple expansion picture predicts, faster by enough that something appears to be missing from the simple account of how the star got from its compact youth to its current enormous size. Signals like this typically come from comparing the width and slight asymmetry of specific spectral lines across multiple observing campaigns rather than relying on a single measurement, since separating a genuine rotation signal from other kinds of motion in the gas requires comparing data gathered at different times with different instruments. Several independent campaigns have converged on a broadly similar conclusion: a surface rotating measurably faster than a single star's evolutionary history alone predicts. One proposed explanation does not involve the star's own history slowing down correctly at all. It involves another star entirely. If Betelgeuse, at some point during its expansion into a red supergiant, swallowed a smaller companion star that had been orbiting close enough to eventually be engulfed, the angular momentum carried by that companion's orbit would not simply vanish. It would transfer into the envelope of the star that absorbed it, adding spin from an entirely separate source on top of whatever the original star carried on its own. A star that inherited extra angular momentum this way would not need its own history to explain unusually fast rotation. It would only need a companion, once present, that is no longer there to be found. In 2008, astronomers watched a binary system called V1309 Scorpii spiral inward and merge in real time, the two stars brightening dramatically as they collided and combined into a single object, an event documented well enough to serve as a direct, observed example of exactly the kind of process being proposed for Betelgeuse's own past, just witnessed as it happened rather than inferred long afterward. A merger like this does not happen instantly. As a giant star's outer envelope expands, a close companion can find itself dragged through the thin outer layers of gas, losing orbital energy to friction with that material, much the way a satellite loses altitude, dragging through Earth's upper atmosphere. The companion spirals inward over time, transferring its orbital angular momentum into the envelope it is plowing through, until it is eventually engulfed completely, leaving behind a single star carrying the spin of what used to be two. A companion massive enough to account for the observed excess would not need to have been particularly large, plausibly something on the order of a fraction of the Sun's mass, modest compared to Betelgeuse itself, but more than sufficient to noticeably spin up the much larger star's outer envelope once fully absorbed into it. An explanation involving a vanished companion also fits naturally with everything already established about Betelgeuse's own mass. A star carrying 15 to 20 times the Sun's mass is itself the product of a complicated formation history, and absorbing one smaller companion along the way would not be a particularly exotic addition to that history, just one more episode in a life already known to be more eventful than the word star tends to suggest. Putting a precise number on exactly how much faster than expected the rotation runs depends heavily on which model of the star's original main sequence spin gets assumed as a starting point, and that starting number is not itself known with much independent confidence. What multiple studies agree on is the direction and rough scale of the discrepancy rather than one precise figure, a rotation that should have been spun down to almost nothing by the sheer scale of the star's expansion, instead still measurably present. Unlike V1309 Scorpii, no observing campaign was watching Betelgeuse during whatever merger may or may not have happened in its past, since any such event, if it occurred, would have taken place long before modern instruments existed to record it. The evidence available now is entirely indirect, a present-day rotation signature interpreted against a hypothetical history rather than a direct observation of two stars becoming one, the kind of case built from circumstantial evidence rather than a confession caught on record. Betelgeuse is not the only red supergiant where a rotation signal like this has been reported, which cuts both ways as evidence. If unusually fast rotation turns out to be common across this category of star, rather than unique to Betelgeuse specifically, a merger explanation tailored to this one object becomes a less satisfying answer, since not every red supergiant studied can plausibly have swallowed a companion of its own. Whether the same puzzle shows up reliably across other stars like it, or whether Betelgeuse stands out as an outlier even among its own kind, remains a question other observing campaigns are still working through. A measurement like this implies the star currently visible on Orion's shoulder may not represent one star's entire uninterrupted history at all, but the merged remainder of two, a companion's entire existence folded invisibly into the structure of whatever survived the encounter. Rotation is not the only kind of evidence a swallowed companion might leave behind. Material from an engulfed star, processed differently than the material native to the absorbing star's own outer layers, can sometimes show up later as a subtle shift in surface chemistry, certain elements appearing slightly more or less abundant than a single star's own uninterrupted history would predict. Searches for that kind of chemical fingerprint on Betelgeuse have so far been inconclusive, neither confirming nor ruling out a merger, the sort of evidence that would need to be unusually clean to settle a question like this on its own, even if it eventually turns up. Confirming any of this requires more than a single spectral signature pointing toward unexpected spin. It requires ruling out every other explanation capable of producing that exact same signal, which turns out to be a shorter list than it might first appear, but not an empty one. A Doppler measurement cannot actually see rotation. It can only see motion along the line of sight, one patch of the disk moving slightly toward the observer, and another patch moving slightly away. True rotation produces exactly that pattern, one edge of the disk approaching as the whole structure turns, the opposite edge receding in lockstep. But true rotation is not the only thing capable of producing that exact signature. Anything that moves part of a star's surface toward an observer while a different part moves away, in roughly the right spatial arrangement, would register as identical data, regardless of whether the star is actually spinning as a coherent body or not. Betelgeuse's surface, already on record as covered by only a handful of enormous convective cells rather than millions of small ones, happens to be in exactly the wrong configuration to rule that possibility out. A rising cell carries hot gas toward the surface and, from Earth's vantage point, slightly toward the observer. A sinking cell, cooling and falling back down nearby, carries gas slightly away. If a rising cell happens to sit on one side of the visible disk while a sinking cell happens to sit on the other, purely as a matter of which enormous cells are active at that particular moment, the resulting pattern of blue shift on one side and red shift on the other looks, to a telescope, indistinguishable from genuine rotation. Stand on a train platform and watch the train beside yours start to glide. For a moment, there is no way to tell, from the sensation alone, whether your own train has started moving or the other one has. The brain has no direct access to absolute motion, only to the relative shift between two things, and it reliably gets the answer wrong until some other cue, a glance at the platform itself, resolves the ambiguity. A telescope pointed at Betelgeuse faces a version of the same problem. It records relative motion across the visible disk, and has no independent way to know whether that motion comes from the whole star turning as one body or from two unrelated convective cells, one rising and one sinking, that simply happen to be sitting in the right places to imitate it. On the Sun, this kind of confusion essentially cannot happen. Millions of individual granules cover the surface at any given moment, rising and falling in every direction, with no particular pattern favoring one side of the disk over another. Whatever velocity signal any single granule contributes gets averaged out across the millions of others doing something slightly different nearby, leaving a clean signal with nothing resembling coherent rotation hiding inside the noise. A star with only a handful of enormous cells does not get that luxury of averaging, the same lack of averaging noted earlier as the reason Betelgeuse's brightness can swing noticeably depending on which cells happen to be rising or sinking at a given moment. The exact mechanism behind one mystery turns out to be a plausible explanation for another. This particular ambiguity is not unique to Betelgeuse, or even to red supergiants generally. Separating rotational broadening from the broader category of motion, astronomers call macroturbulence. Any non-rotational churning of a star's surface gas capable of smearing spectral lines in a similar way is a known, long-standing challenge across stellar spectroscopy as a whole. Betelgeuse simply represents an extreme case of an ordinary problem. A star whose convective cells are so few and so large that the usual workarounds, which rely on averaging across many small-scale motions, stop working as cleanly as they do for smaller, more finely granulated stars. Recent work comparing the interferometric surface maps already discussed, the same reconstructions showing a handful of large, bright, and dark patches, against the spatial pattern implied by the rotation measurements, has found a suspicious correspondence. The patches identified as rising, hotter regions tend to sit on roughly the same side of the disk as the blue-shifted half of the supposed rotation signal, and the cooler, sinking patches line up with the red-shifted half. That correlation does not prove the rotation signal is fake. A star that actually is rotating, with convective cells layered on top, could, in principle, produce a similar-looking overlap by coincidence. But the correlation is close enough that several researchers studying the data now treat at least part of the original rotation measurement as likely convective in origin rather than purely rotational. Telling the two apart cleanly would require watching how the velocity pattern changes over time. Genuine rotation should sweep steadily and predictably across the disk as the star turns, carrying the same blue-shifted and red-shifted regions around at a constant rate tied to one fixed rotation period. A convective pattern should instead drift, strengthen, weaken, and occasionally swap sides entirely as individual giant cells rise, fall, and get replaced by new ones on a timescale of months, matching what was already true of the cells themselves. The two predictions are different enough, in principle, to settle the question with enough patient monitoring. That patient monitoring is still ongoing, and the two camps within the research community have not yet converged. Some studies report exactly the kind of drifting, cell-driven pattern the convective explanation predicts. Others report a signal stable enough over a long enough stretch to look more consistent with steady rotation after all. Both groups are working from real data, gathered with capable instruments, and have not yet reached a shared conclusion, which is a fair description of where the question currently stands, rather than a gap waiting for an obvious answer to be noticed. This uncertainty reaches back directly into the merger hypothesis already laid out. If the convective explanation eventually accounts for most or all of the apparent rotation, the merger idea loses its primary piece of supporting evidence, though it would not be fully eliminated by that alone, since the search for an unusual chemical fingerprint left behind by a swallowed companion remains a separate, independent line of inquiry, untouched by any question about what the velocity data is actually showing. A companion could still have been absorbed at some point in the star's past, even if the specific rotation signal currently cited as evidence for it turns out to be convection wearing a rotation costume, and conversely, the rotation signal could still turn out to be real, even if no chemical trace of a companion is ever found. Claims of detecting rotation in Betelgeuse's spectrum are not new to the past few years either. Tentative rotation signals had been reported in studies going back well over a decade before the merger hypothesis brought renewed attention to the question, generally treated with caution at the time, given the difficulty already known in separating such a signal from ordinary convective motion. What changed more recently was not the discovery of rotation itself, but a specific, testable explanation for why that old, persistent signal might exist without the star actually spinning unusually fast at all. Getting this right matters for more than settling an academic disagreement. A star's true rotation rate feeds directly into models of its internal structure, its magnetic activity, and eventually the way it will collapse once fusion finally stops working in its core. Building an accurate picture of how a star like this ends depends on starting from an accurate picture of what it is doing right now. And right now, one of the most basic properties a star can have, whether or how fast it actually spins, is not something anyone can state with full confidence for the object currently sitting on Orion's shoulder. Neither explanation, rotation, or convection currently settles the matter on its own. What would help is a method that does not depend on Doppler shifts or convective cells at all, evidence pointing toward a companion or its absence through some completely independent channel, the kind of test that would not care whether Betelgeuse's surface happens to be spinning, breathing, or simply rearranging itself in ways that only look like rotation from hundreds of light years away. Betelgeuse brightens and dims on more than one rhythm at once. Underneath the roughly year-long breathing cycle already established, there is a second, much slower pattern layered on top of it, a rise and fall stretched across several years rather than several months. Astronomers call this a long secondary period, a name that describes what it looks like without explaining what causes it. The phenomenon is not unique to Betelgeuse. A large fraction of red giants and supergiants studied closely enough show some version of this same slow secondary rhythm, and after decades of observing it across many different stars, no single proposed mechanism has managed to explain it convincingly in every case. A recent model proposes something Betelgeuse's own data had never specifically required before: a second object. Not a star massive enough to show up easily in any of the measurements covered earlier, but something smaller, lower in mass, orbiting at a distance large enough to take years to complete a single loop, dragging a cloud of dust along with it as it goes. As that companion and its trailing dust swing around their shared orbit, the cloud periodically passes between Betelgeuse and Earth, dimming the starlight slightly on a clock set by the orbit itself rather than by anything happening inside the star. A streetlight sways gently on a perfectly still night, with no wind anywhere nearby to explain the motion. Nothing about the light itself looks wrong up close. The swaying alone is the clue. A small, regular motion with no visible cause, the kind of pattern that, in physics, usually means something is pulling on the object from outside the frame, unseen but inferable from the rhythm it leaves behind. Astronomers have used exactly this kind of reasoning before to find things no telescope of the time could see directly. In the 1840s, the mathematicians Urbain Le Verrier and John Couch Adams independently calculated the existence and position of Neptune, purely from small, unexplained wobbles in the orbit of Uranus, before anyone had ever pointed a telescope at the right patch of sky and confirmed it was there. The planet was found almost exactly where the math said it had to be. Adams's calculations came first, but went unpublished promptly enough that Le Verrier's independent results reached the astronomer Johann Galle in Berlin first, and Galle located the planet within hours of receiving the prediction, a famously fast confirmation for the era. The logic proposed for Betelgeuse follows the same basic shape. Instead of an orbital wobble in a planet's path, the unexplained signal is a periodic dimming with no obvious cause inside the star itself. Instead of a planet, the predicted object is smaller still, low in mass, paired with a trailing cloud of dust, rather than a bare planetary surface. The method is the same. Infer the presence of something unseen from the rhythm it leaves behind, then go looking for it at the moment it should be easiest to find. The model connecting Betelgeuse's long secondary period to a low-mass companion and its trailing dust comes from work led by the astrophysicist Morgan McLeod and collaborators, building on orbital mechanics already used to explain similar dimming patterns in other systems with dusty companions, applied here to Betelgeuse's own timing data. The companion itself is modeled as considerably less massive than the Sun, an object that would never have been bright enough on its own to draw attention, sitting in an orbit wide enough to take several years to complete. Whether it formed alongside Betelgeuse from the same original cloud of gas, or arrived and was captured later, is not addressed by the model, which focuses specifically on the orbital mechanics needed to reproduce the timing already recorded, rather than the object's deeper history. An orbit wide enough to take several years to complete would place the companion at a distance from Betelgeuse, roughly comparable to where Jupiter or Saturn circle the Sun, itself a reminder of how much space the inner part of this particular system already occupies before reaching the companion's own path. The model does more than describe what might already be happening. It predicts something specific and checkable. Based on the orbital period already measured through the dimming pattern itself, the companion should reach its point of greatest angular separation from Betelgeuse, as seen from Earth, sometime around 2027, the moment in its orbit. When it sits farthest from the overwhelming glare of the star, it orbits and is, in principle, easiest to resolve directly with a sufficiently capable instrument. Before that point, the companion sits too close to Betelgeuse's own light to separate the two cleanly. After that point, it begins swinging back inward, closer to the star again, and harder to isolate. Direct imaging of an object, this faint sitting this close to a star this bright, would likely require the same kind of high-contrast interferometric techniques already used to map Betelgeuse's own convective surface, instruments capable of suppressing the glare of the much brighter star enough to let a faint companion register at all, the observational bar deliberately set at the one moment in the orbit when that task is least difficult. If no companion turns up near the predicted position when the window opens, that does not necessarily prove no companion exists, since a sufficiently faint or sufficiently close orbit could still escape detection even at the most favorable moment. It would, however, remove the strongest piece of evidence currently supporting the idea and push the explanation for the long secondary period back toward whatever mechanism eventually accounts for the same pattern in all the other red giants and supergiants that show it without any companion ever being proposed for them. Confirming a companion here would do more than settle one question about one star. Long secondary periods show up across a meaningful fraction of evolved giant stars studied closely enough, and if a hidden companion turns out to be the cause in even one well-confirmed case, it would hand the wider research community its first solid example of what has, until now, remained a pattern without an agreed explanation anywhere it has been found. Long secondary periods have resisted a clean explanation for decades, partly because the leading alternative ideas all carry their own problems. Some researchers have proposed the slow rhythm comes from the giant convective cells themselves, the same handful of structures confirmed earlier as covering surfaces like Betelgeuse's, occasionally clumping or reorganizing on a multi-year cycle. Others have proposed large-scale pulsation modes, distinct from the primary breathing cycle already discussed. None of these ideas has cleanly explained every star that shows the pattern. The same tension already on record between rival explanations for the rotation signal shows up here too. If the convective cells responsible for the star's uneven brightness are also capable of producing a slow, multi-year clumping pattern on their own, a companion stops being strictly necessary to explain the long secondary period, the same way convection alone might already explain away part of the apparent rotation. The companion hypothesis is not the only contender. It is simply the one specific enough to make a concrete, checkable prediction in the near future, which is part of what makes it worth taking seriously regardless of whether it ultimately turns out to be correct. A companion that might be confirmed or ruled out within the next couple of years is not an event reserved for some distant future audience. It falls inside the span of an ordinary human attention, close enough that whoever is listening to this tonight could plausibly still be paying attention when the actual answer arrives, watching the same uncertainty that astronomers are working through right now resolve itself in something close to real time. Every question raised so far, the eruption, the rebound, the rotation, the possible companion, depends on instruments built within the last century, measuring a star most of human history experienced with nothing but unaided eyes and a name. Long before any of this data existed, people were already looking at the same point of light and calling it something, a name that carries its own complicated, much older history, one that has nothing to do with telescopes at all. The original Arabic name for this star translates, most plausibly, to something like the hand of Al-Jaza, Al-Jaza being the older Arabic name for the figure, occupying the part of the sky later identified with Orion. That is not the name anyone uses today. Somewhere between that original Arabic phrase and the word now printed in star charts and pronounced on this channel, a transcription error crept in and never got corrected. Arabic letters distinguish many of their sounds through small dots, placed above or below an otherwise identical basic shape. Dots easy enough to smudge, omit, or misplace when a manuscript is copied by hand, especially across the kind of large-scale translation effort that moved Arabic astronomical texts into Latin during the medieval period. The word for hand, written with a particular combination of those dotted letters, sits uncomfortably close in shape to the word for armpit, written with a different but visually similar combination. At some stage in that copying process, one was mistaken for the other, and the error traveled forward into every translation and transliteration that followed, compounding rather than correcting itself with each new copy. Picture a version of the telephone game stretched across 5 centuries and 3 languages instead of a circle of people in one room. The first person whispers an accurate phrase. By the time the message reaches the last person in line, after passing through dozens of intermediate listeners, each making a small, honest mistake, the final sentence bears only a loose resemblance to the original, and yet everyone downstream of the first error has no way of knowing anything went wrong, because each individual specificated will be accurate to the person making it. The transmission of this star's name worked the same way, except the players were medieval scribes working in different cities, different centuries, and different alphabets, and the final garbled version is the one that survived into permanent use, not because it was correct, but because it was the version still being copied once the copying eventually stopped. The German scholar Paul Kunitz, whose research on the history of Arabic star names remains the standard reference on this kind of question, traced the corruption back through successive medieval manuscripts and concluded the original term almost certainly referred to a hand rather than an armpit, the popular armpit translation itself being a later, secondary attempt to make sense of an already corrupted spelling rather than an accurate rendering of anything the original term actually said. The corruption likely took hold somewhere within the large-scale effort to translate Arabic scientific and astronomical texts into Latin during the medieval period. Much of it centered in cities like Toledo, where scholars worked through enormous bodies of material originally compiled by astronomers writing in Arabic centuries earlier. Star catalogs, in particular, moved through several intermediate steps, copied and recopied by scribes who, in many cases, had no direct familiarity with the spoken language the original names came from, increasing the odds of exactly this kind of small, compounding error slipping through unnoticed. Even the term Al-Jaza itself carries its own layer of drift. In older, pre-Islamic Arabian astronomical tradition, the name appears to have referred to a different figure in the sky than the one eventually associated with it. Only later, as Arabic astronomy absorbed and adapted material from Greek sources describing the constellation now called Orion, did Al-Jaza settle into its more specific, modern association with that particular region of the sky. The star's full name, in other words, carries at least two separate layers of drift stacked on top of each other, not just one. Betelgeuse is not an isolated case either. A meaningful fraction of the star names still used in English today trace back to Arabic originals that passed through the same kind of medieval transcription process, and more than a few carry similar, well-documented corruptions of their own. Names like Fomalhaut and Aldebaran survived the journey with their meanings largely intact. Others picked up errors along the way that, much like this one, nobody ever bothered to formally correct once the corrupted version became the only one anyone used. The pattern is common enough among inherited star names that historians of astronomy treat it as a predictable hazard of the transmission process rather than a surprising exception. Star names were particularly vulnerable to this kind of drift compared to more ordinary vocabulary, since they tended to pass through small, specialized circles of scholars and translators rather than the much larger, more error-correcting pool of everyday speakers who might catch and fix an obvious mistake through routine daily use. A misread word in a popular phrase gets challenged constantly. A misread word in a technical astronomical catalog, consulted by a comparatively small number of specialists, can survive unchallenged for a remarkably long time. Reconstructing a corruption like this is not pure guesswork. Scholars trace it by comparing surviving manuscripts from different periods and regions side by side, looking for the specific point in the copying chain where one version starts to diverge from another, then checking that divergence against the broader vocabulary and spelling conventions known to be standard at that time and place. A single isolated manuscript proves very little on its own. A consistent pattern across many independent copies, all drifting in the same direction at roughly the same historical moment, is what actually allows a scholar to say with real confidence where and how a corruption most likely happened. This is not the first naming problem already on file for this particular star. Its formal catalog designation already turned out to be a holdover from outdated brightness measurements rather than an accurate ranking, assigned to it under the assumption it was the brightest star in its own constellation, when it is not. Its descriptive name turns out to be a copying error several centuries deep. Both labels remain in everyday use, neither one updated to match what is actually true, a coincidence that says less about this one star specifically and more about how slowly inherited names get corrected once they have already settled into place. There is nothing exotic about the underlying mistake. A scribe misread a word, copied it forward, and the error outlived every person involved in making it, surviving centuries of further handling by people who had every reason to trust the version already sitting in front of them. The same basic failure mode shows up in office memos and family stories passed down a few generations, just compressed here into a process that happened to run for hundreds of years instead of a few decades, across languages instead of within one. None of this affects how astronomers actually use the name today. Inside research papers, Betelgeuse functions as a simple label, a fixed string of letters pointing at one specific object, the same way any proper name works once it has been adopted widely enough, regardless of whatever tangled history produced the particular sequence of letters involved. The etymology survives mostly as trivia, a story people enjoy telling at the exact moment someone looks up and asks why the star has such an odd-sounding name, disconnected by now from anything astronomers actually need to know to study the object itself. A name built this way says nothing reliable about the object it points to, only about the people who handled it along the way. Whatever the star is actually doing, the label attached to it has been wrong, or at least imprecise, for longer than anyone alive today has existed to notice. The first time anyone actually looked closely enough to see the star itself, rather than simply repeating its name. The 1920 measurement already established, the one that first pinned a number on Betelgeuse's angular size, produced exactly one piece of information, a single value for how wide the star appeared to be. It did not produce a picture. No texture, no bright or dark regions, no shape beyond a number representing an assumed perfectly even disk. Every star beyond the Sun, observed through every telescope built up to that point and for decades afterward, behaved the same way under magnification, a sharper, brighter point of light, but still fundamentally a point, never an actual surface with anything visible happening across it. That changed in 1995. Hubble's main mirror had launched in 1990 with a manufacturing flaw that blurred its vision considerably, a problem corrected only after astronauts carried out a servicing mission in 1993 to install corrective optics. The Betelgeuse image came only a couple of years after that repair, made possible specifically by an instrument that, for its first 3 years in orbit, would not have been capable of capturing anything nearly this precise. Dupree, working with the astronomer Ronald Gilliland, used the faint object camera aboard the Hubble Space Telescope to capture something no instrument had managed before, an actual resolved image of Betelgeuse's disk, not a calculated width, but a picture with structure inside it. The image, taken in ultraviolet light, showed a disk that was not evenly bright across its surface. A distinct, hot patch stood out clearly on one side, roughly a third of the star's diameter across, far brighter than the surrounding photosphere, the first time anyone had photographic evidence that a star's surface, any star's surface besides the Sun's, was not a smooth, featureless ball of light. The patch ran measurably hotter than the surrounding photosphere, hot enough that its existence was difficult to dismiss as noise or calibration error, and the finding drew significant attention within the astronomical community at the time, covered as a milestone in resolving stellar surfaces generally, not simply as a curiosity specific to one unusually large, unusually close red supergiant. Try reading a book using only the thin strip of light it casts under a closed door. The light tells you the book exists, gives you a rough sense of how bright the room beyond the door must be, even lets you estimate the room's general size from the shape of the light spilling through the gap. None of that gets you the actual words on the page. Opening the door is a different kind of access entirely, the difference between inferring a thing and actually looking directly at it. For every star except the Sun, the door had never been opened. Every telescope before 1995 was reading starlight through the gap under the door, however precisely, never the page itself. Resolving any detail at all on a star this far away pushes against a fundamental limit built into the physics of light itself, the diffraction limit, the smallest angular detail any telescope of a given size is capable of distinguishing, set by the wavelength of light being used and the diameter of the telescope's mirror. Betelgeuse happens to be one of the only stars in the sky with an angular size just barely large enough, combined with Hubble's mirror and the shorter wavelength of ultraviolet light, to sit right at the edge of what was technically achievable in 1995. Shorter wavelengths allow finer angular resolution for a given mirror size than longer, visible wavelengths would, which is part of why ultraviolet light mattered specifically here. Even with that advantage, the resulting image contained only a handful of distinguishable pixels across the star's entire disk, barely enough detail to confirm the bright patch was real and roughly where it sat. A slightly smaller star, or a slightly less capable instrument, and the same attempt would have come back as nothing more than a single, undifferentiated point, just like every star before it. At the time, nobody had a fully worked-out explanation for what the bright patch actually represented. The theoretical picture connecting a feature like this to a small number of enormous convective cells, the framework eventually confirmed through simulation and further interferometric imaging years later, did not yet exist in any developed form. In the years immediately following, the patch was considered for several possible explanations, including the possibility of a localized magnetic hotspot similar to certain kinds of activity seen on smaller, more magnetically active stars, or simply an artifact of how ultraviolet light specifically interacts with the uppermost, thinnest layers of the atmosphere rather than a deeper structural feature. Ruling between these possibilities took years of additional observation, comparing the feature's behavior over time against what each competing explanation predicted. The image arrived first, raising the question. The explanation came afterward, built specifically to account for what the picture had already shown. Astronomy does not always proceed in the tidy order of predict first, observe second. Sometimes the data shows up looking strange, and the theory spends years catching up to explain it properly. Follow-up observations in subsequent years confirmed the feature was not a fluke of a single exposure or an artifact of the instrument itself, since the same kind of asymmetric brightness pattern, shifted somewhat in exact position and shape, kept reappearing in later images, evidence of a real, persistent, if slowly changing, structure rather than a one-time anomaly in the data. Later interferometric imaging, the same VLTI observations already confirmed as eventually mapping a handful of giant convective cells across the disk in detail, built directly on the precedent this first image set, refining a single, confirmed bright patch into an increasingly detailed picture of the star's full surface structure over the following decades. The same scientists behind this 1995 image spent the following decades continuing to study this particular star in close detail, eventually leading the team whose ultraviolet spectroscopy, gathered through the very kind of Hubble observation pioneered here, helped identify the surface mass ejection responsible for the dramatic dimming years later. The image and the discovery were not separate, unrelated achievements by different people working on the same object by coincidence. They were two milestones in one sustained career, spent pointing the same kind of instrument at the same star, decades apart. The achievement also opened a door for other stars, not just this one. Direct imaging of stellar surfaces, once considered essentially impossible outside the Sun, has since been extended, with varying degrees of detail, to a handful of other exceptionally large or exceptionally close stars, though none with quite the same combination of size and accessibility that made Betelgeuse the first candidate to actually succeed. The technique itself, born out of one specific attempt on one specific star, became a method other researchers could point at other targets once it had been proven to work at all. Astronomers had known, in a mathematical sense, that Betelgeuse had a measurable size since 1920. They did not know what its surface actually looked like, in any visual sense. Until 1995, a gap of 75 years between calculating an object's existence in detail and actually laying eyes on it. An image resolves what a single number cannot. It does not resolve everything. The picture itself still depends, at its foundation, on converting an angular measurement on the sky into an actual physical size, and that conversion requires knowing exactly how far away the star sits. That distance was already hinted at as uncertain back when the first angular measurement was taken in 1920, and it has continued shifting in the decades since, for reasons that have nothing to do with the star's surface, its convection, or anything photographed in any image taken so far. Ask how far away Betelgeuse actually is, and the honest answer depends on which decade and which paper supplied the number. Estimates published over the past several decades have ranged from roughly 425 light-years to something closer to 650, a spread wide enough that the star's true distance from Earth has never been pinned down to better than about plus or minus a third of its own value. Every other figure noted earlier in this account, the physical radius, the actual luminosity, the true mass, gets calculated by combining an angular measurement on the sky with an assumed distance. Change the distance, and every one of those downstream numbers shifts along with it, whether or not anything about the star itself has changed at all. The underlying method is called parallax, and it works on exactly the same principle the human visual system uses every waking moment to judge how far away anything actually is. Close one eye, then the other, and a nearby object appears to jump noticeably against the background, while something farther away barely shifts at all. The brain measures that difference in apparent position between two eyes set a few centimeters apart and converts it directly into a sense of depth, all without any conscious calculation required. Astronomers do the same thing on a vastly larger scale. Earth itself becomes the two eyes, observed from opposite sides of its orbit around the Sun, roughly 6 months apart, a baseline of about 186 million miles instead of a few centimeters. A nearby star shifts position against the distant background stars by a small, measurable angle over that 6-month span. A farther star shifts less. The size of that shift converts directly into distance, the same calculation a depth-perceiving brain runs constantly, just scaled up by Earth's orbit instead of the width of a skull. The actual angular shift involved, even for a star as relatively close as Betelgeuse, is tiny, a small fraction of a single arc-second, an angle so small it corresponds roughly to the apparent width of a coin viewed from many kilometers away. Measuring an angle that small reliably sits near the practical edge of what even the most carefully designed astrometric instruments can manage, even before accounting for anything unusual about the particular star in question. Parallax measurements work cleanly for most stars because the star itself behaves, for astrometric purposes, like a single fixed point of light, its position on the sky well defined and stable from one observation to the next. Betelgeuse does not cooperate with that assumption. The same handful of enormous, unevenly bright convective cells already established as covering its surface mean the star's effective center of light, the precise point any instrument actually locks onto when measuring position, shifts slightly depending on which cells happen to be brightest at any given moment. A parallax measurement requires comparing position at 2 points roughly 6 months apart, and if the star's own surface has rearranged itself in the meantime, shifting its effective center along with it, that shift gets tangled up with the actual parallax signal in ways that are extremely difficult to fully separate. The European Space Agency's Hipparcos satellite, which measured parallaxes for over 100,000 stars during its mission in the late 1980s and early 1990s, produced one of the earliest precise distance estimates for Betelgeuse, though the result for this particular star carried unusually wide error bars even within that otherwise reliable catalog, a direct consequence of the photocenter problem already described. The catalog itself was not the final word even on its own terms. A full reanalysis of the original satellite data, published in 2007 by the astronomer Floor van Leeuwen, revised the parallax solutions for a large fraction of the stars in the original catalog, Betelgeuse included, shifting the distance estimate again without any new observations of the star itself, simply through improved processing of data that had already been sitting in an archive for over a decade. Later researchers, working from a different angle entirely, have tried sidestepping the parallax difficulty altogether. A 2020 study, led by the astronomer Meredith Joyce, combined models of the star's internal structure and pulsation behavior with the data already available, arriving at a distance estimate toward the shorter end of the historical range, closer to 550 light-years, than to the larger values some earlier analyses had favored. Pulsation offers one further, largely independent check. Stars that pulsate on a regular cycle, the same basic mechanism already noted as driving Betelgeuse's own roughly year-long breathing, tend to follow a relationship between how long that cycle takes and how intrinsically luminous the star actually is, a relationship well calibrated using other pulsating stars with more reliably known distances. Applying that relationship to Betelgeuse's own measured pulsation period offers a second route to estimating distance, one that does not depend on tracking the star's wandering photocenter at all. An uncertainty of roughly a third sounds modest phrased as a percentage, but translated into physical terms, it means the difference between picturing Betelgeuse as comfortably closer than 500 light-years away or noticeably farther than 600, a gap large enough to matter for any precise calculation built on top of it, even though it changes nothing about how the star actually looks through an ordinary telescope from Earth. A shorter distance does more than shrink one number on a page. Every comparison already made in this account, the radius large enough to swallow 4 planets, the mass running 15 to 20 times the Sun's, the luminosity implied by how bright the star appears from here, all scale directly with whichever distance gets assumed as the starting point. A star placed closer than previously thought has to be intrinsically fainter to produce the same apparent brightness seen from Earth, and a fainter intrinsic luminosity feeds back directly into estimates of mass and evolutionary stage, the same numbers that determine how close the star actually sits to exhausting whatever currently powers it. A star confidently placed closer and fainter implies a meaningfully different position in its own life story than the same star assumed to be farther away and brighter, even though nothing observed about its actual light has changed in the meantime. Every person who has ever reached for a cup without looking directly at it, judged whether a gap was wide enough to step across, or caught a tossed object out of the air, has run a version of this exact calculation thousands of times without noticing. 2 slightly offset views compared automatically into a single working estimate of distance. The same basic trick, run instead across an orbit 186 million miles wide, is what tells astronomers, with real but limited confidence, roughly how far away that point of light on Orion's shoulder actually sits. The eyes doing the comparing are simply much farther apart, and the object being judged is considerably less cooperative than a cup on a table. If the distance itself will not sit still, shifting depending on which convective cell happened to be brightest during a given observing run, then anything inferred about the space surrounding the star, rather than the star itself, deserves the same scrutiny. The region just outside Betelgeuse, where its outflowing material runs into whatever gas already exists in interstellar space nearby, has its own well-known feature, one that for years seemed like one of the more settled, uncomplicated things known about this star. In 2012, the Herschel Space Observatory photographed a set of glowing arcs stretched out in front of Betelgeuse, curving away in the direction the star appears to be moving through space. The astronomer Leen Desin and her team, who captured and analyzed the images, initially interpreted the arcs as a bow shock, a structure that forms when an object moves through a surrounding medium faster than disturbances in that medium can get out of the way. A boat cutting across still water faster than the water's own waves can travel piles up a wedge-shaped wake in front of it, and to either side, water compressed into a wavefront because it physically cannot redistribute itself fast enough to simply slide out of the boat's path. A jet breaking the sound barrier does the same thing to air, compressing it into the shock front responsible for a sonic boom. Betelgeuse, moving through the thin gas and dust-filling interstellar space, appeared to be doing the same thing on a much larger scale, plowing fast enough through the surrounding material to compress it into the arcs Herschel had photographed, a stellar wind colliding with the interstellar medium, the same way a hull collides with water. Herschel observed in far infrared light specifically, the wavelength range where cool dust grains, warmed only slightly by their surroundings rather than by direct stellar heating, emit most efficiently. The arcs themselves are made of exactly this kind of dust, material shed from the star at some point in its past, now drifting through interstellar space far enough from Betelgeuse's direct heat to have cooled down to temperatures that only show up clearly in infrared, essentially invisible in ordinary visible light entirely. The images showed more than a single clean arc. Multiple nested arcs appeared, layered roughly 40,000 years apart in age by some estimates, suggesting a history of repeated mass loss events, rather than one continuous, steady wind. A separate, straight, bar-shaped feature also showed up nearby, oriented at an angle that did not obviously connect to the curved arcs at all, its origin left essentially unexplained even within the original bow shock interpretation. The picture coming back from the telescope was messier and more layered than the clean, single textbook wedge a bow shock diagram usually shows, evidence of a more complicated history playing out in the surrounding material than a simple shock front story alone could fully account for. The arcs themselves sit a considerable distance out from the star, roughly a couple of light years from Betelgeuse by some estimates, far beyond the scale of anything discussed so far in this account, a reminder that the immediate vicinity of a star this large is itself larger than entire planetary systems before even reaching the point where its outflowing material starts interacting with the wider galaxy around it. The original images drew considerable attention at the time, offering one of the clearest pictures yet captured of a red supergiant's wind colliding with its surroundings, frequently used afterward in textbooks and public outreach material as a visual example of exactly what a stellar bow shock looks like, a status now sitting somewhat awkwardly alongside the more recent questions raised about whether the label was the right one to begin with. Whether a bow shock forms at all depends on a specific threshold, not just any relative motion between a star and the gas around it. The relevant comparison is not ordinary sound speed in air, but a related quantity in ionized gas called the magnetosonic speed, the rate at which pressure disturbances can propagate through a magnetized interstellar medium. An object moving slower than that speed disturbs the surrounding gas just as gently as a slow-moving boat ripples calm water without ever forming a true wake, the medium able to adjust and flow around the object instead of piling up into a compressed front. Measuring how fast Betelgeuse moves across the sky draws on the same basic astrometric tracking noted before in connection with the star's distance, watching its position shift gradually against the background of more distant stars over years of repeated observation. That sideways motion, called proper motion, combines with the star's distance to give an actual speed through space, and refining either measurement, distance, or proper motion changes the resulting speed estimate used to judge whether a genuine shock front should even be expected in the first place. Later analysis, working from more refined measurements of Betelgeuse's actual motion through space, raised a specific concern about that earlier picture. The bow shock interpretation requires the star's velocity relative to the surrounding interstellar gas to exceed the local magnetosonic speed, and more careful estimates of both the star's true sideways motion and the conditions in the gas immediately around it suggested the comparison was closer than the original picture assumed, possibly close enough that Betelgeuse may not actually be moving fast enough relative to its local surroundings to produce a genuine shock front at all. If that revised comparison holds up, the arcs Herschel photographed cannot be a bow shock in the strict physical sense, regardless of how convincingly they resemble one in the original images. An object that is not producing a genuine shock front can still leave behind structures that look remarkably similar to one by coincidence. Variations in how much material a star sheds over time can produce shell-like or arc-like structures in its surrounding circumstellar material on their own, layered concentric rings left behind as the rate of mass loss rose and fell across different periods in the star's history, entirely independent of how fast the star itself happens to be moving. Pre-existing structure already present in the interstellar medium, a density variation or magnetic boundary that has nothing to do with Betelgeuse at all, could also produce an arc-shaped feature simply by sitting in roughly the right place relative to the star's position. A boat moving slower than its own bow wave can still drift through water that happens to already be rippled by wind, by a current, by some other vessel's wake from minutes earlier, and an observer glancing quickly might mistake those pre-existing ripples for a wake the boat itself produced. Telling the difference requires looking closely at the actual relationship between the boat's speed and the ripple pattern's geometry, not just noting that a wedge-shaped feature happens to sit somewhere near the boat. The same careful comparison is exactly what more recent analysis of Betelgeuse's arcs has been attempting to carry out. If each arc really does correspond to a distinct mass loss episode roughly 40,000 years apart, the structure preserves a kind of fossil record of the star's recent history, written not in rock layers but in shells of expelled gas and dust, spaced out by however long separates one episode of enhanced mass loss from the next. Bow shocks around other stars have served astronomers as natural laboratories for studying how stellar winds interact with the surrounding interstellar medium under conditions impossible to recreate in any terrestrial setting. Betelgeuse, given its size and relative proximity, had been treated as one of the best available examples of the phenomenon precisely because the structure was so clearly visible and so well resolved compared to similar features around more distant stars. Removing it from that category, even provisionally, matters for more than just one star's individual case history. A textbook example turning out to be the wrong example does not damage the underlying physics of bow shocks generally, well established and confirmed around plenty of other stars where the velocity comparison holds up cleanly. It does mean one of the most frequently cited and most visually striking illustrations of the phenomenon may need to be quietly retired from that role, replaced by a less famous but more reliably confirmed case, the kind of correction that happens in any active field once better measurements become available. Whether or not Betelgeuse is actually moving fast enough to compress the interstellar medium ahead of it remains, like so much else already raised, an open question rather than a settled fact. Added to the list. Whether the rotation signal is real or a trick of convection, whether a companion is actually out there, how far away the star truly sits, whether the arcs in front of it are a shock wave or a coincidence. 4 separate uncertainties, none of them resolved, all converging on a single, much larger question that has been circling underneath everything raised so far without yet being asked directly. Nobody currently knows what stage of its life Betelgeuse is actually in. Not in the vague sense that nobody knows anything for certain, in the specific sense that published models, built by competent researchers working from the same basic physics, disagree with each other by an enormous margin about how much time the star has left before its core collapses. Some place Betelgeuse comfortably in the middle of fusing helium into carbon and oxygen at its core, a stage that, for a star this size, typically lasts on the order of tens of thousands of years, putting any collapse safely beyond the lifetime of anyone currently alive to wonder about it. Others, working from different assumptions about the star's mass, its internal mixing, and its history of mass loss, place it considerably further along into one of the shorter, faster burning stages that precede collapse by centuries rather than millennia. The disagreement does not come from a shortage of surface data. Every measurement already described in this account, the brightness, the convective pattern, the pulsation, the apparent rotation, the possible companion, comes from the outermost few percent of the star's structure, the only part of it light can actually escape from. The core itself, where the fusion stage that actually determines how much time is left is currently taking place, sits buried under a stellar envelope hundreds of times wider than the sun, completely opaque to every form of light that could otherwise carry information out. No telescope built or even seriously proposed can see through that envelope and report back which element is currently burning at the center. The only direct messenger capable of escaping a stellar core promptly is a neutrino, a particle that interacts with matter so rarely it can pass through the entire bulk of a star without being stopped, but the steady trickle of neutrinos produced by ordinary, non-explosive fusion is far too faint to detect from hundreds of light years away with any instrument currently operating on Earth. Stand outside a building at night and hear an unfamiliar sound from inside. Then notice smoke beginning to curl out from under a door. Both signs confirm, beyond any doubt, that something is actively happening within. Neither one, on its own or combined, tells you which stage of that event you are witnessing. The same thin trickle of smoke could mean a fire just starting, still small enough to contain, or a fire already largely burned through its fuel, minutes from extinguishing itself entirely. From outside, with no way to see through the walls, the early stage and the late stage can look almost identical. Every symptom already described in this account, the eruption, the unexplained rebound, the disputed rotation, the possible companion, the questionable shock front, is smoke from underneath the door. All of it confirms something is actually active inside this star. None of it, even added together, tells anyone which stage of that activity is currently underway. The 2020 study already mentioned in connection with the star's distance, combining evolutionary modeling with the star's measured pulsation behavior, argued for the more conservative end of that range, core helium burning with tens of thousands of years still remaining, a conclusion that pushed back against louder, less careful claims that had circulated suggesting collapse might be close at hand. Other published models, built on different assumptions about exactly how much mass the star has shed over its lifetime and how thoroughly its interior mixes material between layers, have not all reached the same conclusion. The honest range across the published literature runs from tens of thousands of years on one end to, in a smaller number of more aggressive analyses, a window measured in centuries on the other, with no current observation capable of definitively closing that gap. Whichever estimate turns out to be closer to correct, every uncertainty already raised, the rotation that might be convection, the companion that might not exist, the distance that keeps shifting, the shock front that might be a coincidence, traces back to the same root cause. They are all attempts to read a story from outside, a building whose interior nobody can directly observe, each one a different kind of smoke curling out from under a different gap in the same closed door. Anyone who has stood outside and watched a storm system visibly building on the horizon, the sky darkening, the air pressure shifting, the wind picking up in a way that unmistakably signals something is coming, while having no real way to know whether the storm breaks in 20 minutes or holds off until well after dark, already carries the basic shape of this particular uncertainty somewhere in the body. Knowing that change is underway and knowing when it concludes are two separate kinds of knowledge, and only one of them is currently available for Betelgeuse. Even the shorter end of the published range, measured in centuries, sits comfortably beyond the concern of any single human lifetime, the kind of timescale that makes the uncertainty itself closer to an intellectual curiosity than anything resembling an urgent threat. Nobody needs to watch the sky tonight, worrying this particular star will do anything at all before morning. The disagreement between models traces back largely to a small number of poorly constrained assumptions buried inside every stellar evolution calculation, particularly how thoroughly convection mixes material between the core and the layers surrounding it, and exactly how much total mass the star has shed across its lifetime through winds and episodes like the eruption already described in detail. Small differences in either assumption compound across the very long stretch of time already spent, fusing progressively heavier elements, and by the time a model reaches the star's current observed luminosity and temperature, those small early differences in assumption have grown into a wide spread of possible answers for what the core is doing right now. Astroseismology, the study of how a star's observed pulsations encode information about its internal structure, offers one of the few indirect windows available, the same basic principle used to study the sun's own interior by tracking sound waves rippling across its surface. Applied to Betelgeuse, the technique has helped narrow the plausible range of models somewhat, favoring the more conservative helium-burning scenario over the most extreme rapid collapse claims, without managing to collapse the full spread of published estimates down to one confident answer. Standing close enough to the building to hear individual creaks and pops from the structure shifting inside, the way astronomers can now track convective cells rearranging and brightness flickering in real detail, still does not grant access to the one room that actually matters, the room where the fire either has decades of fuel left or only minutes. More detailed smoke does not become a window no matter how closely it gets studied. There is an odd asymmetry built into this particular kind of uncertainty. Whatever stage the core is actually in right now, the moment it finally finishes, the signal will arrive at Earth with no advance warning beyond what is already visible, no final countdown beginning days ahead of time, no observable difference between the structure's last ordinary moment and the first moment of its actual end. The only warning anyone will get is the event itself, already underway, light and other signals already in transit toward Earth before any telescope on the ground could have flagged the difference. None of this uncertainty is something this account can responsibly resolve, because it cannot be resolved with the data currently available, and pretending otherwise would mean trading an honest answer for a comfortable one. What can be described with real confidence is not when the ending arrives, but what it will actually look like once it does, the physics of the event itself rather than its timing, a question current science is considerably better equipped to answer than the one just raised. The smoke under the door cannot say whether the fire just started or is nearly finished. It can still say, with real precision, exactly what will happen the moment the door finally opens. The collapse itself, once it finally begins, takes well under a second. A core that has spent its entire functioning life held up by the outward push of fusion loses that support almost instantly once it finishes building a center made of iron, an element that absorbs energy when fused rather than releasing it, the one fuel switch that does not pay for itself. Every lighter element fused before this point released enough energy to hold the core up a little longer. Iron offers no such bargain. Once enough of it accumulates at the center, the core has nothing left to trade, and gravity, which has been waiting the entire time, finally wins outright. With nothing left pushing back, the core collapses under its own gravity, falling inward from a size comparable to Earth down to a sphere only a few miles across in a fraction of a second, before rebounding into the shock wave that will eventually tear the rest of the star apart. That collapse releases an almost unimaginable burst of neutrinos, particles produced as electrons and protons are crushed together into neutrons, particles that interact with matter so weakly they pass through the entire remaining bulk of the star, and through Earth itself, almost as though neither were there at all. In February of 1987, a supernova in a neighboring galaxy called the Large Magellanic Cloud gave astronomers exactly this kind of confirmation. Detectors built to study neutrinos, instruments buried deep underground at facilities including Kamiokande in Japan and another called IMB in the United States, recorded a sudden burst of neutrino interactions, roughly 2 to 3 hours before any telescope on Earth picked up the supernova's visible light. The timing matched the predicted head start closely enough that the event turned a purely theoretical mechanism into confirmed, directly observed physics, the only time a neutrino burst from a core collapse supernova has actually been measured. The neutrinos leave first, and they leave by hours. They escape the collapsing core within seconds and stream outward essentially unimpeded, while the visible shockwave generated by that same collapse still has to physically plow outward through hundreds of times the sun's radius of overlying stellar material before it finally breaks through the surface and releases the light anyone on Earth would actually see. That trip, even moving at a meaningful fraction of the speed of light, takes hours to complete. The neutrinos are not faster than light. They simply do not have to wait. Light from a lightning strike reaches an observer first, since light travels far faster than sound, and the delayed rumble of thunder arrives afterward, the gap between flash and sound translating directly into distance. A star's collapse runs the comparison backward. The neutrino burst, the part of the signal that escapes immediately, plays the role thunder usually plays, arriving first. The visible light, delayed for hours by the shock wave's slow physical journey outward through the star, plays the role of the flash, arriving last, the entire familiar relationship between the two signals flipped by which one actually has to wait. When the light from Betelgeuse's own eventual collapse finally does arrive, current estimates suggest it could briefly rival the full moon in brightness, easily visible during full daylight rather than requiring any darkness at all. A single point of light outshining everything else in the night sky and holding that brightness for weeks before beginning a slow fade lasting months. The visual display would not stay constant throughout. Supernovae typically brighten rapidly over the first days following shock breakout, reach a peak, then decline gradually over the following months, often shifting in color as the expanding debris cools, moving from a brilliant blue-white near peak brightness toward redder tones as the weeks pass, an entire visible evolution playing out for anyone willing to track it night after night, rather than a single instant of brightness that simply switches off. The radius within which a supernova's radiation could meaningfully damage a planet's atmosphere, or biology, is generally estimated at somewhere under 100 light-years, depending on the specific type of event and how directly any beamed radiation happens to be aimed. Betelgeuse sits several times farther away than even the more cautious versions of that danger threshold, comfortably outside any range where its eventual collapse could cause harm beyond an extraordinary light show. The spectacle would be real. The risk would not be. Naked-eye supernovae within our own galaxy are rare enough that only 2 have been documented with any real detail in the past 5 centuries. Galactic supernovae visible without a telescope are estimated to occur only a handful of times per century on average, with most of those hidden from view entirely, blocked by the dust and gas filling the galaxy's own disk between Earth and wherever the event happens to occur. Betelgeuse, sitting comparatively close and largely unobstructed by intervening material, would not suffer that same fate, its eventual collapse guaranteed to be seen clearly rather than lost behind galactic dust the way most such events likely are. In 1572, the astronomer Tycho Brahe observed and meticulously recorded a new star appearing in the constellation Cassiopeia, bright enough to be seen during the day, a sighting that helped overturn the old assumption that the heavens beyond the moon were permanently fixed and unchanging. Just over 3 decades later, in 1604, the astronomer Johannes Kepler documented another such star, visible for the better part of a year before fading from view, the most recent supernova observed within the Milky Way with the unaided eye in the entire span of recorded history since. Tycho and Kepler had no warning either, no neutrino detector buried underground, no centuries of accumulated physics explaining what they were looking at. They simply noticed a new point of light where none had been the night before, wrote down what they saw as carefully as they could, and left a record still being read 400 years later by anyone curious enough to look it up. Modern observers would have one advantage Tycho and Kepler never had. Neutrino detectors operating today, built specifically to catch exactly the kind of burst confirmed in 1987, would likely register Betelgeuse's collapse hours before any visible light arrived, giving astronomers real advance notice, a window to alert observatories and the public alike before the sky itself actually changes. Tycho and Kepler had to discover their supernovae by accident, glancing up on an ordinary night. The next galactic supernova, if it turns out to be this one, may instead arrive with a phone call already in progress. What remains afterward, once the light has faded and the visible spectacle has run its course, depends on details current uncertainty cannot fully resolve. Most likely a neutron star, an object barely wider than a city yet containing more mass than the Sun, packed at a density found nowhere else in ordinary experience, the compressed remains of exactly the core that collapsed in well under a second to set the entire event in motion. A teaspoon of material from an object like that would weigh roughly as much as a mountain, the same basic matter making up an ordinary atom compressed until the space normally separating a nucleus from its surrounding electrons has been crushed away entirely, protons and electrons forced together into neutrons packed edge to edge. An event like this is not only a burst of light, it is also an enormous quantity of matter, the entire outer structure of a star that has existed for millions of years, blown outward into space all at once. That matter does not simply disappear once the light show fades. It goes somewhere, and what it eventually becomes, scattered across the galaxy and incorporated into whatever forms afterward, turns out to connect to something considerably closer to home than anyone watching a distant point of light might expect. The oxygen filling your lungs right now, the calcium holding your skeleton together, much of the iron currently carrying that oxygen through your blood, all formed inside a star, most likely one that ended its life the same way Betelgeuse eventually will. A core collapse supernova does not simply scatter the elements a star happened to build during its lifetime. It cooks up an entire additional batch in the instant of the explosion itself, shock waves slamming through the outer layers fast enough and hot enough to fuse new elements in seconds that would otherwise have taken thousands of years to build through ordinary fusion: oxygen, carbon, neon, magnesium, silicon, calcium, all produced or substantially enriched in that single violent moment, and then flung outward into space, mixing into the surrounding gas that eventually condenses into new stars, new planets, and, eventually, on at least one of those planets, new bodies built from exactly this kind of recycled stellar material. Every calcium atom in human bone, every oxygen atom currently crossing into the bloodstream with each breath, has been through a sequence like this at least once, manufactured inside a star, scattered by its death, and reassembled billions of years later into something that can sit and listen to a story about another star going through the same process. There is a common claim that gets repeated often enough in popular science writing to feel like settled fact, that supernovae are responsible for every heavy element in existence, gold included. That claim is now understood to be incomplete, and the correction is recent enough that plenty of older books and documentaries still repeat the outdated version without anyone having gone back to fix it. In August of 2017, astronomers detected gravitational waves from two neutron stars colliding and merging, the first time such a merger had ever been directly observed, and telescopes around the world turned toward the source within hours, catching the visible and infrared afterglow of the collision in detail. The detection relied on an entirely new way of doing astronomy, combining a gravitational wave signal, a ripple in space-time itself, picked up by detectors called LIGO and Virgo, with traditional light-based observations from dozens of telescopes that raced to find the same event once the gravitational wave alerted them to roughly where and when to look. Confirming what came next required both kinds of evidence together: the gravitational wave establishing that two neutron stars had actually collided, and the light that followed revealing what the collision had actually produced. The light from that afterglow carried a specific spectroscopic signature, evidence of newly formed heavy elements being created and flung outward by the collision itself, elements including gold and platinum in quantities large enough to suggest neutron star mergers, not ordinary core collapse supernovae, may be the dominant source of these particular elements throughout the galaxy. The merger itself took place in a small galaxy roughly 130 million light-years away, called NGC 4993, far enough that the light and gravitational waves recording the event had been traveling since long before anything resembling a human existed anywhere on Earth, a single collision whose afterglow happened to arrive at exactly the right moment for instruments sensitive enough to finally catch it. This does not mean core collapse supernovae, like the one Betelgeuse will eventually produce, contribute nothing to the universe's heavier elements. The process responsible for building the very heaviest atoms, gold and platinum among them, requires an extraordinarily dense flood of neutrons available all at once, conditions some specialized, relatively rare types of supernova may still be capable of producing under the right circumstances. What has changed is the assumption that an ordinary core collapse event, the kind expected from a star like Betelgeuse, can be counted on to deliver that role by default, a confident older claim that newer evidence has made considerably less confident. Not every ingredient in a finished meal comes from the same kitchen, and the elements that make up a human body did not all come from the same cosmic process either. The very lightest elements, most of the hydrogen, and a good share of the helium in existence, formed in the first few minutes after the Big Bang itself, long before any star had assembled. Carbon, oxygen, calcium, and the other mid-weight elements essential to biology trace mostly to stars like Betelgeuse, built up gradually across millions of years of ordinary fusion, and then scattered explosively at the end. Much of the iron specifically traces to a different kind of explosion entirely, the thermonuclear detonation of a white dwarf star rather than a core collapse event, an entirely separate mechanism that happens to also be efficient at producing iron. The heaviest elements of all, the ones once credited almost entirely to supernovae, trace largely to neutron stars colliding, a fourth kitchen altogether. Even the iron actually ejected from a star like Betelgeuse does not come from the same place inside the star that triggered its collapse in the first place. The iron core itself, the structure whose formation set off the entire collapse already described, mostly stays behind, locked inside the neutron star left over from the event rather than escaping into space. The iron that does get flung outward into the galaxy from an explosion like this forms separately and explosively, in the shock-heated layers just outside the collapsing core, radioactive material that decays into ordinary iron only after it has already been ejected, a different batch entirely from the iron that stayed behind and never left. None of this changes what is actually true about the body listening to this right now. The oxygen, the carbon, the calcium, a meaningful share of the iron, do actually trace back to stars that exploded the way Betelgeuse eventually will. What has changed is only the precision of which specific elements get credited to which specific kind of stellar death, an updated, more accurate map of the same basic, still remarkable fact that the material making up a human body was built inside stars long before anyone existed to be built out of it. Carbon shows up in the body's proteins, fats, and genetic material, the literal backbone of the molecules holding every cell together. Calcium does not just sit passively in bone either. It also drives the electrical signals firing through every nerve and muscle right now, including the muscles controlling each breath, bringing more oxygen in. Iron sits at the center of the hemoglobin molecule responsible for carrying that oxygen from the lungs to every other cell that needs it. None of these are decorative details borrowed loosely from astronomy for atmosphere. They are the literal supply chain connecting a body, right now, to a sequence of stellar explosions stretching back billions of years before the solar system itself existed. None of this material moves quickly. An atom ejected from one supernova typically drifts through interstellar space, mixing slowly into surrounding gas clouds, for many millions of years before it ever becomes part of a new star, let alone a new planet capable of eventually assembling something as specific as a human body. The atoms currently doing the work of breathing, circulating, and thinking have had, on average, billions of years and multiple stellar generations behind them before arriving at their current arrangement. Tracking exactly which element came from which kind of explosion took decades of careful, occasionally corrected work, piecing together clues from spectra, from gravitational wave detectors, from laboratory measurements of nuclear physics under conditions no lab on Earth can fully recreate. Modeling the explosion itself, predicting precisely which elements a star like Betelgeuse will actually produce and in what quantities once it finally collapses, runs into a related, even harder problem, one that has nothing to do with what happens after the explosion, and everything to do with how difficult it remains to model what is happening inside the star right now, years before any of this occurs. Modeling a star this size runs into a problem that has nothing to do with missing observations and everything to do with the raw scale of the calculation required. A full three-dimensional simulation of convection inside a red supergiant's envelope has to track gas moving and mixing across an enormous range of sizes at once, from the overall structure of the star, hundreds of times the sun's radius, down to the much smaller scale turbulent eddies that actually carry heat from one layer to the next. Capturing both ends of that range in a single simulation, the largest structures and the smallest meaningful motions, demands a level of computational power that remains well out of reach even on the most capable supercomputers currently available, forcing every research group attempting this kind of simulation to make a trade, sacrificing either the size of the region being modeled or the fineness of the detail captured within it. A global weather forecast works on the same underlying physics that governs every gust of wind moving through a specific mountain pass, and it still cannot reliably predict that one specific gust. The model is correct at the scale it actually operates on. Broad patterns of pressure, temperature, and air movement across an entire continent, built from equations that are not in dispute. What the model cannot do is resolve detail finer than the grid it runs on, typically tens of kilometers across for an ordinary forecast, which means anything smaller than that, a particular gust funneling through one particular gap between two mountains, gets approximated rather than directly calculated. Filled in with an educated estimate standing in for a calculation, the available computing power simply cannot run. Stellar convection modeling runs into the identical problem at a different scale entirely. The broad structure of a star comes out right. The fine turbulent detail inside any single convective cell has to be approximated using simplified rules rather than calculated directly, and different research groups make that approximation differently. The standard workaround, used in almost every full evolutionary model covering a star's entire lifetime, is called mixing length theory, an approximation that treats convection as parcels of gas, rising a characteristic distance before dissolving and mixing with their surroundings, a single adjustable number standing in for the messy, fully three-dimensional turbulence a complete simulation would otherwise have to calculate directly. That single number, the mixing length itself, gets tuned by comparing model predictions against stars whose properties are independently well known, then carried forward and applied to stars like Betelgeuse, where direct calibration is far less certain. The approach itself is not a recent shortcut invented out of desperation. It traces back to ideas borrowed from ordinary fluid dynamics developed in the early 20th century, adapted for stellar interiors decades ago, specifically because a full turbulent calculation was completely out of reach at the time, a workaround that has simply never been fully retired since, even as computing power available for other purposes has grown by an enormous factor. Two research groups using slightly different values for that one adjustable parameter, both defensible, both calibrated against real data, can produce noticeably different predictions for how a star like this evolves through its final stages, exactly the kind of divergence already responsible for the wide range of timelines already discussed. A separate, equally consequential uncertainty involves opacity, the measure of how effectively a given material absorbs and re-emits radiation at a given temperature and density. Opacity values determine how efficiently energy can move outward through a star's interior by radiation alone, and by extension, how much is left over to be carried instead by convection, making accurate opacity data essential input for every other calculation on the table already. Producing those values requires extraordinarily detailed atomic physics calculations, tracking exactly how every relevant element absorbs light across every relevant wavelength, under conditions of temperature and pressure that exist nowhere accessible on Earth. Large, dedicated research efforts, including a project run out of Lawrence Livermore National Laboratory that produced what became known as the opal opacity tables, have spent decades refining these numbers, and meaningful uncertainties still remain in the data, especially under the specific extreme conditions found deep inside an evolved, massive star like Betelgeuse. This is not a problem unique to red supergiants either. Even the Sun, the single best-studied and most precisely measured star in existence, has produced a long-running disagreement between models built using updated opacity and composition data and independent measurements of its internal structure obtained through helioseismology, the study of how sound waves rippling continuously across the Sun's own surface encode information about conditions deep inside it. If opacity uncertainties can still create friction between models and direct measurement for the one star humanity can study in the most detail of all, the same uncertainties applied to a star studied entirely from hundreds of light years away leave considerably more room for disagreement. The specific disagreement involving the Sun is sometimes called the solar abundance problem, a mismatch that emerged after a revised set of measurements in the early 2000s lowered the estimated abundance of certain elements in the Sun's outer layers, bringing spectroscopic measurements into better agreement with each other, but unexpectedly pulling the resulting models out of agreement with the precise internal structure helioseismology had independently measured. 2 decades later, the discrepancy has narrowed but has not fully closed, despite the Sun being close enough, bright enough, and well enough studied, that essentially every other major property of it is known to extraordinary precision. A single, well-resolved three-dimensional simulation covering even a modest patch of a red supergiant's convective envelope run for a simulated stretch of time, amounting to only a small fraction of one actual stellar pulsation cycle, can occupy a dedicated supercomputer for weeks or months of continuous calculation. Extending that same level of detail across the star's entire structure, for anything resembling its full remaining lifetime, sits well beyond what current computing resources can realistically deliver, regardless of how well understood the underlying physics governing each individual calculation actually is. None of this means the problem is permanently unsolvable. Computing power available to astrophysics has grown enormously over past decades, and each new generation of supercomputer pushes the achievable resolution further, allowing simulations that were impossible 10 years ago to run routinely today. Opacity calculations have likewise improved steadily, as atomic physics data gets refined and cross-checked against laboratory measurements and astronomical observations alike. Even substantial increases in available computing power do not solve this kind of problem in a simple, linear way. Resolving twice as fine a level of turbulent detail typically costs far more than twice the computation, a steep, compounding cost that means closing the remaining gap completely may still be a distant goal even after further decades of hardware improvement. Every uncertainty already raised across this entire account, the disputed rotation signal, the unresolved timeline for collapse, the competing explanations for the recent brightening, traces back, at some level, to exactly this limitation. A model that cannot fully resolve convection or pin down opacity with complete confidence inevitably struggles with anything downstream of those two ingredients, which turns out to be nearly everything discussed so far about what is actually happening inside this particular star right now, while its outer layers keep doing whatever it is they keep doing. None of these limitations are being raised to undercut everything already described. They explain why it exists in the current form it does, a set of real, carefully gathered observations interpreted through models that remain imperfect at exactly the points where imperfection matters most. With every limitation now laid out plainly, what remains is to take every separate piece already gathered, the eruption, the rebound, the rotation, the companion, the distance, the arcs, the unresolved internal stage, and set them down next to each other to see what picture, if any, actually emerges. A doctor presented with 5 separate symptoms does not treat each one as its own isolated case file. A single unusual reading, on its own, rarely means much. A second one, unrelated to the first by any obvious mechanism, still might mean nothing more than coincidence. Once enough separate, individually explainable signs accumulate in the same patient, though the working assumption shifts, not necessarily toward a confirmed diagnosis, but toward treating the whole collection as one connected picture worth investigating together rather than 5 unrelated footnotes. Betelgeuse currently presents exactly that kind of file. A surface mass ejection on a scale never before directly measured on any star, larger than anything the Sun has produced by a margin of hundreds of billions. A recovery that overshot every previous brightness record rather than simply returning to normal, brighter now than at any point in over a century of careful tracking. A rotation signal that may be real or may be an illusion produced by its own convective cells, a question current data still cannot settle either way. A possible companion, inferred but not yet seen, with a specific, falsifiable prediction due to be tested within the next couple of years. A core whose actual evolutionary stage no current model can pin down with confidence, leaving the timeline to its eventual collapse actually contested rather than simply unannounced. None of these 5, examined individually, is alarming. Each one has a plausible, often mundane explanation sitting right alongside the more dramatic one. Put together, though, they stop reading like 5 unrelated curiosities and start reading like a single object whose outer layers are behaving with more energy, more asymmetry, and more actual structural change than the standard picture of a quietly aging red supergiant predicts for a star at this stage. A doctor facing a file like this does not walk out of the room and announce a diagnosis on the spot. The next step is almost always more targeted testing, looking specifically for the piece of evidence capable of confirming or ruling out the leading explanation rather than simply restating the same general worry with more confidence than the data actually supports. Astronomers studying Betelgeuse are, in effect, doing exactly that right now. Waiting on the predicted companion observation, waiting on additional years of rotation tracking, waiting on whichever convective cell happens to be active the next time the surface gets imaged again. There is a specific kind of reasoning scientists rely on when no single piece of evidence is conclusive on its own, sometimes described as convergent evidence. The idea that several independent, individually weak signals pointing in the same general direction can add up to something more persuasive than any one of them alone, provided the signals really are independent rather than secretly caused by the same single underlying source. That qualification matters here more than usual. Several of the 5 items just listed are not fully independent of each other. The convective cells described earlier as covering the surface could, in principle, be feeding the rotation signal, the brightness swings, and even some of the difficulty pinning down distance all at once, which means part of what looks like 5 separate confirmations may really be one underlying cause showing up in 5 different measurements rather than 5 truly separate lines of support. None of this, taken together or apart, confirms a collapse is close at hand. Nothing gathered across this entire account establishes a timeline shorter than the conservative estimates already laid out, tens of thousands of years remaining under the most cautious published models. What the full collection does establish, with reasonable confidence, is that Betelgeuse is not behaving like the placid, slowly cooling giant the word red supergiant tends to conjure. It is shedding unprecedented amounts of material, brightening past its own historical records, possibly spinning in ways its own physics struggles to account for, possibly hosting a companion nobody has directly seen, and resting on top of a core whose internal state remains, by the honest admission of the people studying it most closely, unknown. A few specific developments would shift this picture meaningfully. Direct confirmation, or ruling, out of the companion around the predicted observing window would resolve one entire branch of the uncertainty outright. Several more years of stable, undrifting rotation data would weigh against the convective explanation and back towards something closer to real spin. A second eruption on anything like the scale of the first would turn an isolated event into an established pattern rather than a one-time anomaly. A confirmed chemical signature of a swallowed companion, the kind of evidence already mentioned as still inconclusive, would shift the picture further still, supporting a merger history independent of whatever the rotation data eventually shows. Each of these possible developments tests a different piece of the file separately, the kind of staged, specific follow-up that real scientific caution looks like in practice, rather than a single experiment expected to settle everything at once. Until one or more of those specific things happens, the honest state of the evidence stays exactly where this account has left it: suggestive, connected, and still unresolved. Concluding that a star is more active and less well understood than older models assumed is itself a real, useful scientific result. The kind of finding that redirects future observing time, future computing resources, and future theoretical effort toward exactly the open questions that actually matter, rather than toward questions the data has already quietly settled. Most real progress in astronomy looks like this: a slow narrowing of honest uncertainty rather than a single dramatic announcement, even when the underlying subject happens to be as dramatic as a star, possibly approaching the end of its life. Noticing several small, separately explainable things, and only later recognizing they belong to the same underlying pattern, is not a habit unique to astrophysics. It happens whenever someone looks back across a stretch of time and realizes a handful of small, previously unremarkable changes, a routine shifting slightly, a few minor decisions that seemed unconnected in the moment, a pattern of small absences or small additions, were actually all symptoms of the same single thing happening underneath the whole time, visible only once enough of the individual pieces had accumulated to be looked at together rather than one at a time. The instinct to connect scattered observations into a single story is not a scientific superpower. It is closer to an ordinary, occasionally unreliable, deeply human reflex, one astronomers simply apply with more discipline and more willingness to say clearly when the connection does not yet hold up. Step back from the file entirely, and what remains is a single point of light, the same one visible tonight from anywhere with a clear view of Orion, sitting exactly where it has always appeared to sit, doing whatever it is actually doing, indifferent to every model ever built to explain it. Nothing in this account changes what shows up by simply looking up. The light arriving right now left the star long before any of the measurements just described were ever taken, carrying none of this debate along with it, simply a point of warm, reddish light completing the same physical journey it has been making for centuries. 5 lines of evidence, 2 competing explanations for almost every one of them, a core nobody can see, and a model that cannot fully resolve its own convection, all of it sitting quietly behind a single, steady point of light that looks, to anyone glancing up tonight without any of this context, exactly the way it always has. Whatever Betelgeuse turns out to actually be doing, underneath every disputed signal and every cautious model, it remains, tonight, a star hanging quietly over one shoulder of a hunter, waiting to be looked at by anyone willing to step outside or simply close their eyes and picture it there, somewhere between 4 and 6 centuries ago. Depending on which distance estimate from earlier in this account turns out to be closer to correct, a photon left the surface of Betelgeuse and began crossing the empty space between that star and Earth. That photon carried no information about anything described tonight. Not the eruption, not the rebound, not the rotation nobody can confirm, not the companion nobody has seen. It simply traveled, in a straight line, through several hundred years of vacuum, unaffected by time in any way that would mean anything to it, until it reached the upper atmosphere of this particular planet, passed through it largely undisturbed, and arrived at the surface of an eye. The lens of that eye bent its path slightly, focusing it down onto a patch of tissue lining the back of the eyeball, the retina, where it struck a single photoreceptor cell built specifically for this purpose. A molecule inside that cell, shaped to respond to exactly this kind of arrival, changed shape the instant the photon's energy was absorbed, and that change triggered a cascade of chemical signals ending in an electrical pulse sent down the optic nerve toward the brain. That is the entire physical mechanism of seeing a star, not a metaphor standing in for something else. A real photon, centuries old, ending its entire journey by being absorbed by one real cell, built from the same kind of atoms already discussed tonight, in a body assembled from elements forged in stars, not unlike the one this particular photon just left. A point of light, this faint, viewed at night, is caught mostly by the eye's rod cells rather than the cone cells responsible for color and daylight vision, which is part of why a dim star at the edge of visibility tends to look slightly more vivid out of the corner of the eye than when stared at directly, an old quirk of human anatomy that has nothing to do with the star and everything to do with how rod cells happen to be arranged across the retina. Whatever Betelgeuse is actually doing right now, in whatever year it currently is by the star's own clock rather than Earth's, this account cannot say with certainty, and neither can anyone studying it professionally. The star might be quietly continuing to fuse helium at its core, with tens of thousands of years still ahead of it. It might be considerably further along than that, the timeline measured in centuries rather than millennia. Nobody currently knows which, and nothing about tonight depends on the answer. The light reaching this exact eye, on this exact night, was already centuries old before any of the measurements discussed tonight existed, before the people who made those measurements were born, in some cases before their countries existed. Whatever changes the star is or is not currently undergoing will not arrive here, in any form, for centuries more. There is no honest way to ask what Betelgeuse is doing right now, not in any sense that includes both the star and the person listening to this. Right now, for the eye receiving this particular photon, is a single, specific moment. Right now, for the star, is a moment hundreds of years removed from this one, already finished, whatever it held. Two different events, separated by an old and very real gap, sharing nothing but the single photon that managed to cross the distance between them and complete, after a journey longer than recorded measurement, the one specific task it had left to do. Breathe in, slowly, and notice it without trying to change it. Some of the oxygen entering on that breath was built inside a star very much like this one, at some point in the deep past, scattered by an explosion, drifted for millions of years through space, eventually pulled into the cloud of gas that became the sun and the planets, and eventually into a body capable of breathing it in on a particular night while listening to a story about another star going through something similar. The eyes, whether open and resting in darkness or already closed, are built from that same general inventory of recycled stellar material. The retina that would catch this exact photon, if the eyes happen to be open and pointed at the right patch of sky, is doing its quiet, automatic work constantly, with or without attention, the same way it has every night a person has ever fallen asleep underneath a sky full of old light. Nothing about tonight requires staying awake to verify any of it. The star will still be there tomorrow, behaving however it is currently behaving, and the body listening to this will still be made of exactly the same recycled material, whether or not either one is being watched. Every question raised across this account is still exactly where it was left, unresolved, waiting on more data, more years, more careful observation. That is not a failure of the story just told. Most of what is actually true about the universe arrives this way. Slowly, through patient accumulation rather than a single dramatic reveal, and very little of it actually requires resolution before a person can rest easy with it. Knowing exactly what Betelgeuse is doing right now is not actually necessary for anything that matters tonight. The not knowing has been the entire shape of this account from the very first line, an old, stubborn point of light refusing to resolve cleanly no matter how many instruments get pointed at it, and that refusal turned out to be more interesting, not less, than a tidy answer would have been. A star that fit every model perfectly would have made a shorter story and a less honest one. The heart beating right now took its most recent beat in a fraction of a second, built from elements that took millions of years to assemble and scatter and reassemble into working tissue. The room holding this body, whatever room that happens to be, sits on a planet orbiting a star that itself eventually formed from material very much like what Betelgeuse is scattering into space right now. On the star's own clock, the same basic process, simply running on a time scale too long for any single lifetime to watch start to finish. Tonight is one small, ordinary moment inside a process that has been running, in various forms, for longer than this planet has existed. Orion itself, the full shape of it, rises and sets across the sky the same way it always has, the same outline ancient observers traced with their own names, long before any of the physics discussed tonight existed to explain what they were looking at. That shape will still be there tomorrow night, and the night after, completely unconcerned with whether tonight's particular account of one of its stars holds up under future scrutiny or needs revising once better data finally arrives. This account opened by asking whether star was even the right word anymore for an object behaving this unpredictably. It probably still is. Stars have always been allowed to misbehave by exactly this kind of degree: eruptions, pulsations, rotations real or only apparent, all of it well within what the physics governing a star's life actually permits, even when it looks alarming from several hundred light years away. What changed across this account was never the definition. It was only how closely anyone had bothered to look. It does not need anyone awake to keep doing whatever it is currently doing. Thank you for spending this much time with one complicated, still uncertain star, and for staying with every open question this account was honest enough to leave open. Whatever Betelgeuse turns out to actually be, it will still be there the next clear night, and the one after that, completely unbothered by how long anyone takes to fall asleep underneath it. Rest well. Good night.